Out in the silent, deep expanse of space, there are monsters. Not the kind from stories or nightmares. These are real, and they're quietly breaking the laws of the universe as we know them. Tonight, we're not here to be terrified. We're here to wonder. We're here to drift through a story written in the stars, a gentle exploration of a cosmic enigma that's questioning the very rules of reality. What happens when a black hole, an object defined by its bottomless appetite, grows so large and so fast that it just shouldn't exist? And what does its quiet, impossible presence tell us about the story of our universe? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Join me as we journey across billions of light years, to the dawn of time itself, to meet a monster that's growing faster than physics should allow. This isn't a story of cosmic horror. It's a story of profound mystery, and of the beautiful, unfolding process of scientific discovery. Imagine a set of rules. A cosmic speed limit. It's a fundamental law that governs how quickly anything in the universe can grow, born from the delicate balance between two of nature's most powerful forces, gravity and light. For black holes, these rules are everything. They set the pace for their feasting, a natural break that keeps them from growing too quickly. Now, what if we found something that was ignoring this rule entirely? What if we found a black hole that was flooring the accelerator, consuming matter at a rate our physics says is impossible? And what if, while doing so, it was shining in a way it shouldn't be, sending out signals that contradict our best ideas of how these cosmic engines work? Recently, astronomers pointed their telescopes toward the faint light of the early universe and found just that. A monster in the dark. A paradox. An object that is somehow too bright, too hungry, and too powerful to be real. And yet, there it is. This is the story of an extreme black hole, and it begins not with a bang, but with a quiet question whispered across the cosmos. How do you grow a giant when you're not given enough time? The Cosmic Rulebook, Understanding the Standard Black Hole. Before we can appreciate the rulebreaker, we first have to understand the rules. Our journey starts with the familiar, yet still deeply strange, concept of a black hole. At its heart, a black hole is simply a place where gravity has become so powerful that nothing, not even light, can escape. Think of space-time as a stretched-out rubber sheet. A star like our Sun creates a small dimple. A more massive star creates a deeper one. Now imagine an object so incredibly dense that it punches a hole straight through that fabric, creating a well of gravity so deep it becomes a point of no return. That's a black hole. This point of no return is called the event horizon. It's not a physical surface you could touch, but an invisible boundary. Cross it, and your fate is sealed. The journey is a one-way trip toward the singularity, a point of theoretically infinite density where our known laws of physics just fall apart. For most of their lives, black holes are relatively quiet. Stellar mass black holes, born from the collapse of massive stars, might be just a few times the mass of our Sun. Then you have the giants. The supermassive black holes that live at the center of nearly every large galaxy, including our own Milky Way. These titans can be millions, or even billions, of times the mass of the Sun. Our own galaxy's central black hole, Sagittarius A*, is a respectable 4 million solar masses. But how do they get so big? They eat. A black hole grows by pulling in matter. Gas, dust, even entire stars that wander too close get caught in its gravitational grip. This material doesn't fall straight in. Instead, it forms a vast, swirling structure called an accretion disk. Picture a cosmic hurricane of superheated plasma, spinning at incredible speeds. As this material spirals inward, friction and gravity heat it to millions of degrees, causing it to shine with an intensity that can outshine entire galaxies. This is what we see as a quasar, the brilliantly luminous heart of a young galaxy, powered by a feeding supermassive black hole. The light from a quasar is one of the most powerful things in the universe. It's a beacon that lets us see these objects from across cosmic time. But that same light is also its own cage. It creates the very rule that our extreme black hole seems to be breaking. This rule is called the Eddington limit. Sir Arthur Eddington, a brilliant astrophysicist in the early 20th century, realized that the intense radiation blasting out from a feeding black hole exerts its own pressure, a form of light pressure. Think of it as a hurricane of pure light. As gravity pulls matter in, this radiation pressure pushes it out. The Eddington limit is the point of perfect balance. It's the theoretical maximum speed at which a black hole can steadily eat. If it tries to gobble up matter any faster, the outward pressure of its own light becomes so intense that it literally blows away its incoming food. It's a natural kill switch. Gravity says, eat, and light says, stop. The Eddington limit is the compromise. It's the cosmic speed limit for growth. This has been a cornerstone of black hole physics for decades. It explains why the supermassive black holes we see today aren't all infinitely large. Their growth was controlled. And this is where our mystery truly begins, because the Eddington limit gave astronomers a serious timing problem. When we look deep into space, we're also looking back in time. The light from the most distant quasars has traveled for over 12 billion years to reach us. This means we're seeing them as they were when the universe was just a toddler, less than 1 billion years old. And what we found there was baffling. We found supermassive black holes that were already billions of times the mass of the Sun. How was that possible? According to the Eddington limit, even if a black hole started growing right after the Big Bang and fed continuously at the absolute max speed, it just wouldn't have had enough time to get that huge, that quickly. The math didn't add up. It was like finding a fully grown redwood tree that was only a few years old. For years, astronomers wrestled with this paradox. How did the universe's first black holes get so big, so fast? Two main ideas came about. First, maybe they didn't start small. Maybe in the early universe, massive clouds of gas could collapse directly into heavy seeds, black holes already born with the mass of thousands of suns, giving them a head start. The other idea is more radical. What if, for brief, frantic periods, black holes could somehow cheat the Eddington limit? What if they could have short, violent growth spurts, gorging on matter way faster than the rules allow? This idea, called super-Eddington accretion, was a great theory, but finding proof was incredibly hard. To solve the mystery, scientists needed to do more than just find a big black hole. They needed to catch one in the act of breaking the law. And in the faint, ancient light from a quasar 12 billion light-years away, a team of researchers believes they've done just that. The anomaly. A monster in the early universe. In astronomy, a breakthrough often begins with a single point of light that doesn't quite fit the pattern. For a team of researchers from Japan, that point of light came from the Subaru telescope. Perched atop Mauna Kea in Hawaii, Subaru's massive mirror can stare deep into the cosmic past, capturing the faint whispers of the infant universe. While looking through data from distant quasars, they focused on one in particular. To us, it's just a name in a catalog, but in reality, it's a brilliant beacon of light from a time when the universe was only about 1.5 billion years old. A fossil, a snapshot of a galaxy in its youth, powered by a ravenous black hole. The team used a technique called spectroscopy. By splitting the quasar's light into a spectrum of colors, like a prism, they could read its cosmic barcode. This barcode reveals the chemistry, temperature, and motion of the gas swirling around the black hole. One thing they looked for was the magnesium-2 line. The way this line was broadened by the chaotic motion of gas in the accretion disk allowed them to do something amazing: to weigh the black hole. Their calculations pointed to a giant, already hundreds of millions of times the mass of our Sun. This was big, but not unheard of for that early time. The real shock came when they calculated how fast it was growing. By analyzing the sheer brightness of the quasar, they could figure out the rate at which it was eating. The more matter a black hole consumes, the brighter its disk shines. When they ran the numbers, they got a figure that seemed impossible. The black hole was pulling in matter at 13 times the Eddington limit. Let's just pause on what that means. This wasn't just bending the rule, it was shattering it. Imagine a speed limit of 60 miles per hour. This object was clocked at 780. The self-regulating mechanism that should have choked off its fuel supply had completely failed. The outward blast of radiation, which should have been blowing its food away, was being totally overpowered by gravity and the torrent of matter falling in. It was force-feeding itself at a rate that defied explanation. That alone would have made it one of the most extreme objects ever found. But the universe is rarely that simple. The mystery was about to get deeper, because this black hole wasn't just breaking one rule. It was breaking several, all at once. Our models of how black holes work make certain predictions. When a black hole starts eating this fast, in a state of super-Eddington accretion, the structure of its accretion disk should change. The immense pressure should puff up the inner part of the disk, making it thick and bloated. And that bloated disk should, in theory, block our view of the very central region. From that central region, two other key signals are born: a powerful jet of particles and a glow of high-energy X-rays. Many feeding black holes launch colossal jets of plasma from their poles, funneled by intense magnetic fields and flung out at nearly the speed of light. We can detect these jets through the radio waves they emit. This black hole was radio loud. It was firing a powerful jet. At the same time, right outside the event horizon, is a region of incredibly hot plasma called the corona, like the black hole's scorching atmosphere. This corona is what produces huge amounts of high-energy X-rays. This black hole was also incredibly bright in X-rays, meaning it had a vibrant, active corona. And here's the paradox. According to the leading models, you can't have all three at once. The bloated, puffed-up disk you'd expect from this feeding frenzy should disrupt the magnetic fields needed to launch a jet. It should also block and dampen the X-rays coming from the corona. Models predicted that as a black hole ramped up its eating past the Eddington limit, its radiojet and X-ray glow should flicker and die. This black hole didn't get the memo. It was doing everything at once. It was 1. Growing at 13 times the theoretical speed limit. 2. Firing a powerful, radio-loud jet. 3. Shining with unexpectedly bright X-rays. It was a cosmic contradiction, a rule breaker on an epic scale. The scientists knew they were looking at something special. They weren't just observing a black hole, they were observing a state of being that had only ever been a theory. They were seeing a monster in the middle of a binge, and it was shining a light on one of the biggest questions in cosmology. The journey of discovery. Catching a monster mid-sheet. The publication of these findings in *, the Astrophysical Journal, was a huge moment, but it was the kind that raised more questions than it answered. This wasn't just about a single, weird object. It was a potential key to finally solving the mystery of how the first supermassive black holes even exist. Let's go back to that timing problem. Those billion solar mass black holes in the infant universe have been a major headache for scientists. The Eddington limit seemed to put an unbreakable ceiling on growth that just didn't fit with what we were seeing. So, finding an object that so clearly violates this limit is the first direct proof that super-Eddington accretion isn't just a theory, it's a real way for black holes to grow incredibly fast. This one object suggests that the universe's first black holes didn't grow steadily. Instead, their lives might have been marked by brief, chaotic, and incredibly violent feasts. It's like a live fast, die young mentality on a cosmic scale. For a few million years, a blink of an eye in cosmic time, a black hole might run into a massive stream of cold gas. This sudden buffet could overwhelm the Eddington balance, kicking off a phase of runaway eating. The team behind the discovery proposed exactly this. They believe they've captured a black hole in a rare, transitional phase. They aren't seeing a stable state. They're seeing a temporary, gluttonous burst. This could be triggered by something like two galaxies merging, which would funnel enormous streams of gas right to the center, giving the black hole an all-you-can-eat opportunity. This sudden gas burst idea also helps explain the contradictions. Maybe in this fleeting state, the accretion disk hasn't had time to settle into the bloated shape our models predict. Maybe the system is so chaotic that the magnetic fields somehow hold on and launch a jet, even as the disk swells. And maybe the corona is being energized in a new, unexpected way by this frantic flow of matter. We are essentially watching a system caught in a moment of profound change. We're seeing the exception that reveals a new set of rules we didn't even know existed. The technology that made this possible is just as incredible as the discovery itself. The Subaru telescope's ability to scan wide patches of the sky was key to finding this rare object. Instruments then dissected the light with the precision needed to weigh the black hole and measure its appetite. This was then combined with data from other telescopes, like X-ray observatories in space, to build a complete picture. Each wavelength of light tells a different part of the story. The visible light tells us how fast it's eating. The radio waves tell us about the jet, and the X-rays tell us about the extreme environment right at the edge. Only by combining all these pieces can we see the full, paradoxical picture. This discovery also shines a light on something fascinating about modern astronomy. We often think of space as static, but it's a dynamic, evolving place. Objects change, and sometimes, they change on timescales we can actually see. We are moving from taking still photos of the universe to creating a dynamic film of its evolution. We're starting to see black holes not as fixed objects, but as living engines whose behavior changes over time. This particular black hole is a window into a critical, yet poorly understood, chapter of cosmic history. It's a laboratory for testing physics under the most extreme conditions imaginable. It's helping us answer that fundamental, chicken or egg, question. Do galaxies control the growth of their black holes, or do black holes control their galaxies? The immense energy blasting from a black hole like this could have a huge impact, potentially blowing gas out of the host galaxy and shutting down star formation.
By studying this, we're watching the architecture of galaxies being forged. The journey is far from over. This is just one object. The next step is to find more like it. Are these rule breakers common in the early universe, or are they incredibly rare? Do they all have this strange combination of features? Answering these questions will require even more powerful tools, like the James Webb Space Telescope, whose infrared vision is perfectly suited to peering into the dusty cradles of the first galaxies. For now, this single, distant point of light has given us a tantalizing glimpse. It has shown us that the universe is more creative and more chaotic than our neat models might suggest. It has shown us that to grow the giants of the cosmos, you might first need to learn how to break the rules. Exploring these cosmic mysteries is what drives us forward. It's a journey we take together, one question at a time. If you're captivated by the quiet wonders of the universe and enjoy these gentle explorations into science, consider subscribing. Every new discovery opens up a new story to tell, and by joining our community, you won't miss the next chapter. Your support lets us continue diving into the science that makes us all look up at the night sky and wonder. So, we find ourselves back where we started, in the quiet of deep space, thinking about a monster. But maybe, monster, is the wrong word. A monster is something to be feared. This object is something to be understood. It's a puzzle, a paradox, and a profound clue to our own cosmic history. We've journeyed across 12 billion years, from the fundamental laws of physics to a place where those laws are being pushed to their breaking point. We've seen how the elegant balance of gravity and light sets a cosmic speed limit, and how the universe, in its youthful energy, found a way to cheat. This extreme black hole, growing 13 times faster than it should, all while firing a jet and glowing with X-rays it isn't supposed to have, is more than a celestial curiosity. It's a clue. It is direct evidence that helps solve the riddle of how supermassive black holes got so big, so quickly. Their growth wasn't a slow, steady march. It was a series of frantic, chaotic bursts, brief moments of cosmic gluttony that reshaped the galaxies around them. What we've learned tonight is that the universe isn't always a place of calm, predictable order. It's also a place of violent transitions and beautiful contradictions. It builds its most magnificent structures not just by following the rules, but through moments of glorious rebellion against them. As you drift off to sleep, think of that distant point of light, a silent testament to a time of cosmic giants, a time of impossible hunger. It's not a story that should keep you awake with fear, but one that can fill you with a sense of wonder. Because it reminds us that even in the deepest, darkest corners of the cosmos, there are stories unfolding that challenge everything we think we know. It reminds us that the universe is still full of secrets, quietly waiting in the dark, ready for us to find them. And the quest to understand them is one of the most beautiful stories of all. Part 2. What makes a black hole truly extreme? After meeting a black hole that seems to grow faster than the universe should allow, the question begins to change. At first, it sounds simple. What is the most extreme black hole ever found? But the longer you stay with that question, the stranger it becomes. Because in astronomy, extreme is not always one thing. Sometimes it means the largest. Sometimes it means the fastest. Sometimes it means the brightest, the earliest, the hungriest, or the most violently influential. And sometimes the most extreme object is not the biggest one at all. Sometimes it is the one that forces scientists to admit that the old rules were too small for reality. That is part of what makes black holes so quietly fascinating. They do not compete in only one category. They are more like different kinds of cosmic records. One may be so massive that the mind struggles to picture it. Another may spin so fast that space-time itself is dragged around with it. Another may launch jets of matter across distances so large they begin to feel more like geography than motion. Another may appear so early in cosmic history that it should not have had enough time to exist in the form we see it. And when people ask for the most extreme black hole, what they are often really asking is something deeper. They are asking where the universe seems to stretch furthest, where nature looks least ordinary, where the familiar rules begin to tremble. So for a little while, let's slow that question down. Instead of trying to name a winner too early, let's understand the categories. Because once you see the different ways a black hole can become extreme, the whole story becomes much richer and much more mysterious. And by the end of this chapter, the idea of one single champion may feel less important than the strange landscape of extremes itself. The first and most obvious kind of extreme is mass. This is the kind most people imagine first. They picture a black hole so enormous that it dwarfs every ordinary comparison. Not a dead star a few times heavier than the Sun, and not even the black hole at the center of our own galaxy, which is already about 4 million times the Sun's mass. They picture something truly unreasonable. According to NASA's current black hole reference page, the most massive black hole observed is Ton 618, with an estimated mass of about 66 billion suns. That is the kind of number that stops behaving like a number and starts behaving like weather. It is so large that language begins to fail, because the brain evolved to deal with hills, rivers, faces, storms, perhaps cities at most. Not with invisible objects tens of billions of times heavier than the star that built the daylight of Earth. And yet even a number like that can slip past us if we hear it too quickly. So it helps to sit with it. Our Sun contains about 99.8% of all the mass in the solar system. Everything else, the planets, the moons, the asteroids, the dust, all of it together is just the leftover fraction. Now imagine something with not one sun's worth of mass, but 66 billion suns. Not glowing like a star, not spread across some obvious visible surface, but concentrated into an object defined by gravity so intense that even light cannot escape once it crosses the boundary. This is one version of extreme. It is the extreme of scale. Not chaos, not motion, not brightness, but sheer, overwhelming weight. But mass is only one way to become extraordinary. Because a black hole can also be extreme by the time in which it appears. This is a quieter kind of shock, and in some ways an even deeper one. NASA notes that one of the most distant known black holes is in the galaxy QSOJO 31311806, around 13 billion light-years away. And Webb observations have also confirmed actively growing supermassive black holes in galaxies seen less than 600 million years after the Big Bang. These early systems matter because when we see them, we are not just seeing distance. We are seeing youth. We are seeing the universe when it was still very young, still in its first chapters, and yet somehow already producing black holes that seem far too mature for their age. That is where the question becomes more unsettling. A black hole in the nearby universe can be given billions of years to grow. There is time for mergers, time for feeding, time for the slow work of gravity. But in the early universe, time is the missing ingredient. If a black hole already seems huge when the cosmos is still young, astronomers have to ask an awkward question. How did it get there so fast? Did it begin from a bigger seed than expected? Did it feed at a rate that pushed beyond the usual limit? Did the early universe offer growth conditions unlike the ones we see around us now? A black hole that appears too early is extreme not simply because of what it is, but because of when it is. Its existence becomes an argument against our easy assumptions. And then there is appetite. This may be the most dramatic category of all, because hunger is easier to imagine than mass. A black hole itself is dark. You do not see the hole directly. What you see, when it is feeding, is the violence around it. Matter falling inward does not simply disappear politely. It swirls. It compresses. It heats. It forms an accretion disk so energetic that the region around the black hole can shine with absurd intensity. Quasars, those brilliant galactic cores, are powered by supermassive black holes devouring matter at extraordinary rates. NASA describes quasars as distant galaxies whose bright cores are powered by supermassive black holes, sometimes producing between 10 and 100,000 times the luminosity of the Milky Way from a region only light days to light years across. That is worth pausing over too. Our galaxy contains hundreds of billions of stars. It is vast, slow, and luminous in the patient way galaxies are luminous. Yet a quasar can outshine all of that, not because it contains more stars in that tiny region, but because gravity is doing something more efficient and more brutal. Matter falling into the grip of a black hole converts gravitational energy into radiation with astonishing power. In other words, extreme hunger can make darkness appear brighter than a galaxy. This is where the idea of the Eddington limit becomes so important. There is supposed to be a kind of balance. As matter falls in and the disk grows brighter, the outgoing radiation pushes back. At some point, the black hole should begin to fight its own meal. Too much brightness should make further feeding harder. But that limit, elegant as it is, has never fully ended the mystery. Recent Chandra observations described a quasar called RACSJO 32035, seen only about 920 million years after the Big Bang, whose black hole appears to be growing faster than the usual Eddington limit, with estimates around 2.4 times that limit. In other words, at least some black holes do not always eat politely. Some appear to lunge. And that matters because the black hole from the first chapter of this story was not just large. It was not just bright. It was behaving like a rule breaker. That is one of the most important distinctions in this whole topic. A black hole may be extreme because it is the biggest thing in its class. But it may be even more interesting if it is extreme because it breaks the pattern. Because once a black hole begins to grow faster than the safe, theoretical pace, it stops being a record and becomes a clue. Another kind of extreme is spin. This one is easy to underestimate because spin sounds almost playful, as if the black hole were merely turning in place. But rotation, at these scales, is not a small detail. It changes the structure of spacetime around the black hole. It affects how close matter can orbit before crossing the final boundary. It influences jets, accretion, energy release, and the whole mood of the system. NASA notes that all black holes spin, and on its current overview page it lists GRS 1915 plus 105 as the fastest known black hole, rotating more than 1,000 times per second. That is a stellar mass black hole, not a supermassive one, but it shows how extreme the category of spin can become. When you move to supermassive black holes, the numbers are expressed differently, but the strangeness remains. ESA has described the supermassive black hole in NGC 1365 as spinning at almost the speed of light. That does not mean the entire black hole is a solid object whipping through space like a wheel. Black holes do not have surfaces in the ordinary sense. But it does mean the rotation is so intense that the region around the black hole is profoundly affected. Space and time themselves are dragged into the rotation, a phenomenon that makes the inner environment of a spinning black hole even more bizarre than the non-spinning case. There is something almost poetic about this category of extreme. Mass is heavy. Appetite is violent. But spin is elegant. It is the difference between a silent abyss and a twisted one. It reminds us that black holes are not simply holes. They are engines with character. Their rotation carries history. It may tell us whether they grew slowly through steady feeding, or whether they were shaped by mergers and turbulent cosmic encounters. A spinning black hole is not just dramatic. It is biographical. And then we come to jets, which may be the most visually dramatic expression of black hole extremity. It is one of the great ironies of astronomy that one of the darkest things in the universe can help create some of its longest and most energetic beams. Near a feeding black hole, matter does not always fall inward quietly. Some of it is somehow redirected and launched outward in narrow, powerful jets that travel for astonishing distances. NASA describes monster black holes as particle accelerators capable of launching material to near light speed. And Chandra has recently reported distant black holes with jets more than 300,000 light-years long, with particles moving at roughly 92 to 99% of light speed. That is another kind of record altogether. A black hole can be extreme not because of how much it keeps, but because of how much it throws back into the universe. The jet becomes a kind of announcement. It can cross scales that feel almost geographic. 100,000 light-years is already difficult to picture. 300,000 begins to feel less like an astronomical feature and more like a structure of the cosmos itself. And when those jets move near light speed, they are no longer just side effects. They are major events in the life of a galaxy. NASA has also noted that powerful quasar jets appear to be tied not only to rapid spin, but to bright X-ray coronas and strong magnetic fields. In other words, a black hole may be extreme because several ingredients come together at once. Not just a lot of mass, not just a lot of fuel, but a particular combination of spin, magnetism, and energetic surroundings that lets the system organize itself into something fierce and narrow and fast. If you step back, a pattern begins to emerge. The universe does not hand out one crown for extremity. It hands out many. The most massive known black hole is one thing. The farthest known black hole is another. The earliest rapidly growing systems are another. The fastest spinners, the most powerful jets, the brightest quasars, the most aggressive feeders, all of them belong to different corners of the same strange family. And this is why the original question becomes both harder and better. What is the most extreme black hole ever found? The honest answer may be that it depends on which edge of reality you care most about. If you care about sheer mass, ton 618 is hard to ignore. If you care about early arrival, the black holes seen in the young universe become deeply unsettling. If you care about rate of growth, the super-Eddington systems are among the most important. If you care about the twisting effects of spin, then rapidly rotating black holes begin to take center stage. If you care about how far a black hole can reach into the surrounding cosmos, then the great jets become the real spectacle. Each of these is a different form of extremity, and each one tells us something slightly different about how the universe works when gravity is allowed to become almost absurd. There is another layer here too, one that is easy to miss. The most extreme black hole may not always be the one with the most dramatic number beside its name. Sometimes the most important extreme is the one that changes theory. Astronomy is full of large things. But not every large thing creates a crisis. A black hole becomes especially valuable when it forces science to revise the story. When it appears too early, grows too quickly, shines too strangely, or launches jets in a way that theory did not quite expect, it stops being just a record holder and becomes a teacher. That may be the quiet beauty of this subject. We begin by looking for the champion, but what we really find is a map of the limits of understanding. Every extreme black hole marks a place where nature becomes difficult to summarize. And maybe that is why they feel so compelling even to people who do not usually follow astrophysics closely. They are not just objects. They are edges. They are places where the ordinary logic of everyday life no longer helps much, and where the universe begins to speak in a different accent. If you are enjoying the slow journey so far, this is a gentle moment to like the channel, subscribe, and maybe leave a comment about which kind of black hole extreme fascinates you most. The biggest one, the fastest one, the earliest one, or the strangest one. It is always interesting to see which mystery pulls people in most strongly. For now, though, maybe the most calming conclusion is also the simplest one. A black hole does not have to win every category to feel impossible. Even one category is enough. A darkness heavier than billions of suns is enough. A hunger brighter than a galaxy is enough. A rotation that drags spacetime is enough. A jet flung across hundreds of thousands of light years is enough. An early universe black hole that appears before it should is enough. The word extreme does not point to one object so much as one feeling. The feeling that nature, when left to its own devices, is capable of becoming far stranger than our first intuition ever imagined. And that leaves us in an interesting place. Because now that we understand the categories, the next question becomes more focused. If mass is the category most people mean when they ask for the most extreme black hole ever found, then perhaps the next step is to meet the true heavyweight in calmer detail. Not just as a number on a list, but as a real cosmic object with a history, a location, and a scale so vast it almost dissolves into abstraction. That is where the story naturally wants to go next. Not just into the general idea of extreme, but toward the giant that is so often named whenever this question is asked. The black hole that seems less like an object and more like a cosmic boundary marker. The kind of thing that makes even other supermassive black holes feel modest. And once you arrive there, the question shifts one more time. Not, what is the most extreme black hole? But how can something like that exist at all? Part 3. Meeting the giant called ton 618. Now that we've slowed down and looked at what extreme can really mean, the story naturally narrows toward one name. A name that appears again and again whenever people ask about the most extreme black hole ever found. A name that sounds less like an object and more like a code, a distant signal, a quiet label pinned onto something so enormous it almost resists being called a thing at all. Ton 618. If you have never heard that name before, that is perfectly fine. In a strange way, it makes the experience better. Because Ton 618 does not need any mythology around it. It is already mysterious enough. It does not need dramatic music. It does not need exaggeration. It only needs patience, a little time, a little imagination, and the willingness to sit with a scale so large that even black holes, already among the most extreme objects in nature, begin to look small by comparison. When astronomers talk about Ton 618, they are usually talking about mass. Pure, crushing, unreasonable mass. This is the category where Ton 618 becomes difficult to ignore. It is often described as one of the most massive black holes ever identified, with estimates placing it at tens of billions of times the mass of the Sun. And once you hear that, the first reaction is often not understanding. It is numbness. Because numbers that large do something odd to the mind. They stop feeling real. They flatten into abstraction. They become labels rather than experiences. So it helps to approach it more slowly. Our Sun is already unimaginably large compared with Earth. It contains almost all the mass in the solar system. Jupiter, Saturn, Earth, Mars, the moons, the asteroids, the dust. All of it together is only a tiny leftover compared with the Sun itself. And yet Ton 618 is not a few suns. It is not a few thousand suns. It is not even a few million suns, which would already place it in the company of the giant black holes at galactic centers. It is a black hole with a mass so large that the comparison begins to feel unfair. If our Sun were a single grain of sand, Ton 618 would not be a hill. It would be a coastline. And yet, for all of that mass, Ton 618 is not visible in the ordinary way people imagine. That is one of the most fascinating parts of black holes. The object itself is dark. You do not really see the black hole. What you see is the region around it. The light comes from matter caught in the grip of its gravity, spiraling inward, heating up, glowing with ferocious intensity as it approaches the final boundary. So in a sense, our first meeting with Ton 618 is not with the hole itself, but with its appetite, with the brilliant turmoil that gives away the presence of something far darker underneath. This is why Ton 618 is associated with a quasar. And quasars are among the brightest things in the universe. That phrase can pass by too quickly, so let's let it rest for a moment. One of the brightest things in the universe. Not one of the brightest stars. Not one of the brightest galaxies in the ordinary sense. But one of the brightest known phenomena anywhere. A quasar is what happens when a supermassive black hole is actively feeding, and the disk of matter around it becomes so hot and so luminous that it can outshine the galaxy hosting it. That is the kind of environment we are dealing with here. Ton 618 is not a quiet black hole sitting politely at the center of a galaxy, minding its own gravity. It is, or at least was when the light left it, an active cosmic engine. A dark center wrapped in brilliant violence. A black hole announcing itself not through shape or color, but through energy. And perhaps this is the first important shift in perspective. When people hear about the biggest black hole, they often imagine something like a cosmic marble, just larger and larger and larger. But Ton 618 is not just a bigger version of a simple idea. It is part of a whole system, a feeding system, a luminous system, a dynamic system. The extremity is not just in the number attached to it. It is in the fact that such a number belongs to an object that is still involved in the restless physics of growth, heat, motion, and light. To understand just how strange that is, it helps to remember that black holes do not begin as giants. At least, not in the ordinary story. A stellar black hole is born when a massive star collapses. It may begin with a mass several times that of the Sun, perhaps tens of suns in some cases. To go from that to something like ton 618 requires an almost unthinkable history of feeding and merger and survival. It means the black hole did not just exist. It built itself. Or perhaps more accurately, the universe built it, slowly and violently, over unimaginable stretches of time. And that leads to a beautifully difficult question. What does it mean for something to grow that large? Not just in a mathematical sense, but in a physical one. How does the universe make a black hole that outweighs so many entire ideas of scale? Does it grow steadily, year after year, age after age, like a tree adding rings? Does it feast in bursts? Does it merge with other giants? Does it live through epochs of famine and then suddenly find itself in the path of a flood of gas? The truth is that astronomers are still piecing together the full story. But ton 618 exists as proof that whatever route nature takes, it is capable of building things much larger than our intuitions would comfortably predict. There is something else worth noticing too. Ton 618 is not famous because it is nearby and easy to study. It is famous because it is distant. The light we receive from it has traveled for billions of years. That means we are not seeing ton 618 as it is now, in any ordinary sense. We are seeing ancient light, old testimony, a message that began its journey long before Earth was remotely close to its current moment in history. There is something very calm and humbling about that. To look at an object like ton 618 is to look into both distance and time at once. It is to remember that astronomy is always a form of patience. We never receive the universe immediately. We receive it delayed, filtered through light, offered to us long after the event. So when we speak of ton 618, we are speaking partly in the present and partly in the past. We are speaking about a giant whose light has crossed the cosmos to reach us. A giant that may have changed since that light began its journey. A giant we know only through the evidence it left behind in its radiation. And still, even with all those layers of uncertainty and distance, the impression remains overwhelming. Ton 618 is one of those rare cosmic objects that makes the phrase, supermassive black hole, feel almost too casual. It forces a second look at the word supermassive. It asks whether we are using language that is strong enough. Because at some point, the usual categories become too tidy for the thing they're trying to describe. Ton 618 does not merely sit at the heavy end of a scale. It lives at the edge where the scale itself starts to look insufficient. If you try to picture the event horizon of such an object, the mind begins to drift a little. And that is understandable. The event horizon, again, is the boundary beyond which nothing can escape. For a black hole as massive as ton 618, that boundary would be enormous. Not because the black hole is fluffy or spread out like a cloud, but because gravity on that scale creates a region of no return that extends across a truly vast distance. In smaller black holes, the event horizon might be tiny by astronomical standards. In something like ton 618, the sheer scale becomes almost atmospheric. Not something like a point, but something like a domain. There is a strange calm in thinking about that. Not because it is safe, of course. Nothing about black holes is safe in the ordinary sense. But because once an object becomes that immense, it stops feeling like an accident. It begins to feel almost geological, almost architectural, less like a violent event and more like a permanent feature of the deep universe. A place where gravity has gathered itself into one of its most complete expressions. And yet the story is not only about size. This matters. Because if ton 618 were only large, it would already be extraordinary, but perhaps not as hauntingly interesting as it is. Part of what makes it linger in the imagination is that it sits at the intersection of several kinds of extremity. It is massive, yes. It is associated with quasar-level brilliance, yes. It is distant, ancient in the light by which we know it, yes. But above all, it feels like a cosmic answer to a question we did not quite know how to ask. How far can gravity go? How much matter can one dark center command? How luminous can darkness become when fed enough fuel? How absurd can the universe be while still remaining real? TUN 618 does not answer these questions in words. It answers them by existing. There is a temptation, when talking about something so large, to become overly dramatic, to treat it like a monster, or a villain, or some kind of cosmic horror. But there is another way to hold it in the mind, a quieter way. TUN 618 is not evil. It is not malicious. It is not lurking. It is simply a natural consequence of a universe that allows gravity to persist, to gather, to pull, to shape, and to keep shaping for ages beyond human scale. It is one of the forms that patience can take in a violent cosmos. And maybe that is why objects like this fit so well into the calm rhythm of a sleep channel, even though they are built from extremes. Because there is something strangely soothing about being reminded how large reality is. Not because largeness solves our problems, but because it reorders them. The mind that spends all day moving through deadlines and notifications and small human noise suddenly finds itself considering an object tens of billions of times the mass of the sun, far away in the dark, wrapped in ancient light. And for a moment, everything personal loosens a little. The world becomes larger than urgency. If this slow journey into the deep universe is helping you unwind, this is a quiet place to like the video, subscribe to the channel, and maybe leave a comment about where you're listening from tonight. It is always nice to imagine these ideas drifting out into so many different rooms, cities, and quiet corners of the world. Now, as calm as this all sounds, TUN 618 also carries a more challenging message. Because once you accept that something this massive exists, another question rises very naturally behind it. Not just what it is, but how it got that way. A black hole like TUN 618 does not simply appear in a finished state. It must have a past, a history of feeding, a history of becoming. And when astronomers try to reconstruct those histories, the universe becomes less cooperative. Because making a black hole this large is not easy, even on cosmic timescales. You need matter, of course. Huge amounts of it. Gas falling inward over long stretches of time. Mergers between galaxies, perhaps bringing their central black holes with them. More feeding after the merger. More time. More gravity. More survival. But even when you give the universe all of that, there is still a sense that the biggest black holes live right near the edge of what seems plausible. Not impossible, clearly, because TUN 618 is there, but uncomfortable. As if nature reached this result by taking the long route through chaos. This is where TUN 618 becomes more than a record holder. It becomes a challenge to imagination. Because it asks us to think not only in terms of huge outcomes, but in terms of huge durations. Billions of years, continents of time, generations of stars forming and dying, galaxies interacting, gas falling inward, light being produced, matter disappearing beyond the boundary. All of that, somehow, feeding the same dark center. And through all of it, TUN 618 remains hidden in the most literal way. The black hole itself never becomes visible. It stays what black holes always are. A center defined not by what it shows, but by what cannot return from it. Even at the upper edge of cosmic extremity, black holes keep their nature. The more massive they become, the more the surrounding universe speaks for them. That is, in its own way, a beautiful restraint built into reality. The most powerful objects do not reveal themselves directly. They reveal themselves through influence, through orbit, through heat, through light from matter not yet lost, through the structure they impose on everything nearby. They are known by their consequences. And perhaps that is why TUN 618 leaves such a strong impression. It is not only the size. It is the combination of invisibility and power. An object of almost inconceivable mass, known through the brilliance of the chaos around it. A darkness so deep that it can become one of the brightest things in the universe, not by shining, but by forcing everything near it to shine before it disappears. If Part 2 helped us understand the categories of extremity, then Ton 618 gives the idea a face, or at least the closest thing a black hole can have to one. It is the heavyweight. The giant, the name that returns whenever the question is asked in its simplest form, and whether it holds that title forever or not is almost secondary. Because even if one day another black hole is found to be larger still, Ton 618 has already done its work. It has shown us what the upper edge begins to feel like. It has shown us that a black hole can become so large that it stops sounding like an astrophysical detail and starts sounding like a feature of the universe itself. And that brings us gently to the next stage of the story. Because once you meet a black hole like Ton 618, once you allow its scale to settle in the mind, the next question becomes irresistible. Not, is it large, because clearly it is. Not even, is it extreme, because clearly it is that too. But rather this. How can something that massive ever be born and sustained at all? That is where the mystery deepens. Because a giant like Ton 618 does not only stretch the imagination, it stretches the story of how black holes grow. Part 4, how something that massive can even exist. After meeting a giant like Ton 618, the question becomes less about awe and more about origin. Not because the awe disappears, but because it starts to sharpen into curiosity. A black hole that massive does not feel like a random accident. It feels like the result of a very long story. A story written in gravity, fed by time, and shaped by the slow, patient mechanics of the universe. And yet, the moment you ask how something that large can exist, the universe becomes slightly incooperative. Because black holes are already strange when they are small. A dead star collapses. Gravity wins. Matter is squeezed into an object so dense that even light cannot escape beyond a certain boundary. That alone is enough to sound unreal. But a black hole like Ton 618 is not just a collapsed star. It belongs to the family of supermassive black holes, the giants found in the centers of galaxies, and astronomers know that these objects must form and grow very differently from ordinary stellar black holes. NASA notes that supermassive black holes have masses above 1 million suns and that observations strongly suggest they sit at the hearts of nearly all large galaxies. That is where the mystery begins. Because if supermassive black holes are not simply oversized versions of stellar black holes, then what are they, really? Not in the poetic sense, but in the historical sense. What path does the universe take to build one? How do you go from some early seed, whatever that seed may be, to a dark gravitational giant powerful enough to outshine galaxies when it feeds? At first glance, the answer seems simple. Time. Give gravity enough time, enough matter, and enough opportunity, and perhaps a black hole can just keep growing. It can swallow gas, dust, unlucky stars, maybe even merge with other black holes, slowly becoming something larger and larger until, over billions of years, it reaches the enormous scales we observe. And to some extent, that is true. Growth by feeding is real. Growth by merger is real. Black holes do gain mass by drawing in matter from their surroundings, and galaxies do collide and reshape one another across cosmic history. Their central black holes may eventually spiral together and merge as well. NASA's overview of supermassive black holes reflects this broader picture. These giant black holes reside in galactic centers, are fed by infalling material, and their growth is tied to the larger story of galaxies themselves. But the simplicity only lasts for a moment. Because once astronomers started looking deep into the universe, and therefore deep into the past, they found supermassive black holes that were already very large when the universe was still young. And that changed the tone of the whole discussion. A very massive black hole in the nearby universe is impressive, but not impossible to imagine. It has had billions of years to grow. There has been time for accidents, time for mergers, time for gas to fall inward, time for the slow work of gravity to pile one chapter onto the next. But a very massive black hole in the early universe is a different kind of problem. It arrives before the story feels ready for it. ESA's black hole overview puts this tension very plainly. Astronomers have observed supermassive black holes in the early universe where, on the ordinary timeline, they would not have had enough time to grow from small stellar mass black holes. That simple sentence contains a quiet crisis. Not a crisis of observation, because the black holes are there, but a crisis of explanation. If they exist, then something about our easy picture of black hole growth is incomplete. This is one of the great strengths of astronomy. It does not let us keep stories just because they're comfortable. It keeps showing us objects that refuse to fit. And so the question of how something like Ton 618 can exist becomes part of a larger scientific puzzle. Not merely how one giant formed, but how the universe ever learned to build giants at all. There are a few main ideas, and each one feels, in its own way, both reasonable and slightly unsettling. The first is the most familiar. Start small, then grow. In this picture, a black hole is born from the death of a massive star, and then over time it gains mass. It feeds. It waits. It feeds again. It merges with others. It survives long enough to become something immense. There is a certain calm logic to this. Nature often builds large things from smaller beginnings. Mountains rise from long pressure. Reefs grow from countless tiny bodies. Trees stand because they kept adding one quiet layer after another. So it is tempting to imagine a supermassive black hole as simply the end result of persistence. And yet the early universe seems to warn us that persistence alone may not be enough. That brings us to the second possibility. Perhaps some black holes did not begin as small stellar remnants at all. Perhaps some began much larger. ESA points to this idea by suggesting that the answer to early giant black holes is likely to involve medium-sized, or intermediate mass, black holes, because they can grow more quickly into supermassive ones. In other words, maybe the universe sometimes gives itself a head start. Instead of beginning with a tiny seed and hoping for impossible growth, it may begin with a much heavier one. That possibility is deeply interesting because it changes the emotional rhythm of the story. It says that maybe the universe did not cheat the timeline. Maybe it changed the opening move. Maybe under the right early conditions, huge clouds of gas could collapse in ways that produced large black hole seeds from the beginning, avoiding the long climb from ordinary stellar mass. This idea often leads people to imagine the early universe as a place much stranger than the one around us now. And in some ways, it was. Denser, younger, more crowded with raw material, less settled. A place where galaxies were still assembling, where structure was still forming, where gravity had access to oceans of gas that had not yet been used up by generations of stars. In such a universe, the route to a giant black hole may have been less like gardening and more like weather. Less gentle accumulation, more collapse. Still, even a larger seed does not explain everything. A bigger beginning helps, but it does not eliminate the need for growth. Eventually, a black hole still needs fuel. It still needs to eat. And that leads to the third major idea, which is perhaps the most dramatic of all. Maybe some black holes go through brief episodes of extraordinary feeding. Not steady, balanced feeding, but extreme, almost frantic bursts. NASA reported in 2024 on a low-mass supermassive black hole called LID 568, observed only about 1.5 billion years after the Big Bang, that appears to be pulling in matter at more than 40 times the theoretical Eddington limit. NASA described this kind of feast as potentially crucial for explaining how supermassive black holes grew so quickly in the early universe. That is a profound clue. Because the Eddington limit, in its calm mathematical way, is supposed to act like a regulator. As a black hole feeds and grows brighter, the outward pressure of radiation should begin to push back against incoming matter. It is, in a sense, a built-in brake, a cosmic reminder that there should be some balance between appetite and resistance. But if some early black holes can feed far above that limit, even briefly, then the whole timeline of growth changes. A black hole no longer has to climb at a safe, polite pace. It can leap. And perhaps that is the real answer, or at least part of it. Perhaps the universe does not build its largest black holes through one single mechanism. Perhaps it uses several. A somewhat larger starting seed, combined with dense early environments, combined with mergers, combined with short periods of feeding so intense that older limits become more like suggestions than barriers. There is something beautifully realistic about that possibility. Real things are often not built by one clean explanation. They are built by several processes working together over time. A city is not the result of one decision. A forest is not the result of one season. A life is not the result of one turning point. Why should a giant black hole be any simpler? Another important part of this story is the relationship between black holes and galaxies. For a long time, it was tempting to think of the black hole as merely something sitting inside the galaxy, like a dark object in the middle while the rest of the galaxy gets on with the real business of stars and gas and light. But that view has changed. NASA has reported that the biggest black holes in the universe can grow faster than the rate at which stars form in their host galaxies, suggesting that black hole growth and galaxy evolution are deeply linked, and not always in the tidy, proportional way people once imagined. That matters because it means a black hole does not just live inside a galaxy. It helps shape the galaxy's fate. When a black hole feeds intensely, it can release astonishing amounts of energy into the surrounding environment. Jets can blast outward. Radiation can heat gas. Winds can push material away. In some cases, this may even make it harder for the host galaxy to keep forming stars in the same way. The black hole becomes not just a consumer, but an architect, a violent influence in the central politics of the galaxy. So now the question becomes even more interesting. To ask how something as massive as Ton 618 can exist is also to ask what sort of galaxy, or what sort of chain of galaxies and mergers and gas flows, could support such an existence. A giant black hole may need not only time and matter, but a surrounding environment willing to keep delivering both. And maybe this is where the story becomes easiest to imagine. Not as one black hole sitting alone in the void getting larger for no reason, but as part of a galactic ecosystem. Gas falls toward the center. Stars are born, live, and die. Galaxies drift, collide, and merge. Central black holes grow, perhaps merge too. New gas funnels inward. Bright phases come and go. Some periods are quiet. Some are explosive. Over immense timescales, one center becomes more dominant than the others. More fed. More massive. More difficult to ignore. Eventually, if enough of these chapters line up, you get something like Ton 618. But even after saying all of that, the mystery is not fully dissolved. Because the truth is that astronomy is still piecing together which of these routes matters most, under which conditions, and at what stages of cosmic history. NASA's Hubble team has described a rapidly growing black hole found only 750 million years after the Big Bang as a crucial, missing link between young star-forming galaxies and the first supermassive black holes. That phrasing is important. A missing link. It tells us that the story is not yet complete. We have some of the chapters. We do not yet have all of them. And there is something strangely comforting in that. The universe is not only large enough to humble us, it is large enough to keep teaching us. A black hole like Ton 618 can feel overwhelming because it is so much larger than human scale. But it is also reassuring in a quieter way, because it reminds us that reality is still deeper than our summaries of it. We are not done learning the structure of the world. That may be why these objects stay in the mind so long. They are not just large. They are unfinished explanations. They are invitations to think more carefully. You can imagine, if you like, the history of a giant black hole not as one continuous feeding session, but as a long biography. An early beginning in a dense young universe. A period of growth. A merger. A brighter phase. A quiet phase. Another inflow of gas. Another jump in mass. More time. More structure forming around it. More stars in the host galaxy. More violence in the center. More light from the accretion disk. More matter crossing the boundary forever. All of it happening so slowly that no human life could ever perceive the full arc, and yet all of it still part of one coherent life story written in gravity. In that sense, a giant black hole is not a moment. It is an accumulation. It is what happens when the universe keeps saying yes to the same process for a very long time. And yet, the story of growth also changes the way we think about scale. Because ton 618 is not just large in the way a mountain is large. It is historically large. It carries the weight of everything that had to happen before it could become itself. Every inflow of gas, every galactic interaction, every favorable condition, every period of survival, all of it is hidden inside the final number. When astronomers estimate the mass of a giant black hole, they are not just measuring an object. They are glimpsing the result of a very long cosmic memory. That may be the most beautiful way to think about it. A black hole is memory. Not memory in the human sense, of course, but in the structural sense. A stored record of what gravity has been allowed to do over time. If this slow unfolding of the story is helping you settle in, this is a soft place to subscribe, like the video, or leave a comment with the black hole question that fascinates you most. Sometimes the best part of these journeys is seeing which mystery keeps people awake in the best possible way. For now, though, one more gentle thought seems to rise from all of this. The existence of a giant black hole does not only tell us that gravity is powerful. We already knew that. It tells us that gravity is patient. That the universe is capable of building some of its most astonishing structures through long histories we can only partly reconstruct. Not always neatly. Not always at the speed our theories expect. But somehow, over time, with enough matter and enough opportunity, the giant appears. And once it does, the next question becomes less about how it formed in general, and more about what it does to everything around it. Because a black hole that massive does not just sit at the center of a system without consequence. It changes the story of its galaxy. It changes the motion of nearby matter. It changes the light. It changes the future of stars around it. And in some cases, it may even change what the galaxy itself is allowed to become. That is where the journey wants to go next. Not just to the birth of the giant, but to its influence. Because the most extreme black holes are not only remarkable for what they are remarkable for what they do. Part 5, the disk of fire around the darkness. If a black hole were only dark, it would be much harder to love as a mystery. It would still be important, of course. Still strange. Still one of the most unsettling ideas in all of science. But it would remain hidden in a more complete way. Silent. Invisible. A gravitational secret with very little to say about itself. Instead, nature does something more interesting. Around many black holes, especially the giant feeding ones, darkness becomes surrounded by brilliance. The black hole itself does not shine. It cannot. But the matter falling toward it can shine with such violence that the region around it becomes one of the brightest places in the universe. And that is one of the great paradoxes at the heart of this story. Some of the darkest objects known can create some of the brightest spectacles known, not because the darkness glows, but because everything near it is pushed into a final, luminous struggle before it disappears. To understand what the most extreme black holes are really like, you have to understand this glowing region around them. You have to understand the disk of fire around the darkness. At first, it helps to imagine what would happen if matter simply dropped straight into a black hole. You might picture a cloud of gas drifting inward, falling neatly through the event horizon, and vanishing without much fuss. But the universe is almost never that tidy. Matter in space is usually moving already. It has momentum. It has direction. It does not simply fall straight down like a stone into a well. Instead, when gas, dust, and other material are drawn toward a black hole, they begin to orbit. They circle. They flatten into a disk. And as more matter joins that disk, the whole structure becomes denser, faster, hotter, and more chaotic. This is the accretion disk. A wide, swirling, rotating system of matter spiraling inward toward the black hole. The closer that matter gets to the center, the faster it has to move to remain in orbit. Inner parts of the disk race around more quickly than outer parts. That difference creates friction, turbulence, and collision. The gas is compressed. It rubs against itself. It heats to extraordinary temperatures. And that is when the light begins. This is an important shift in tone, because when people hear the phrase black hole, they tend to imagine emptiness, pure absence. But a feeding black hole is not an empty scene. It is a scene of overwhelming activity. The black hole may be silent, but the matter around it is not. It glows. It screams in radiation. It becomes a laboratory of heat and motion. A place where gravity converts infalling matter into light with astonishing efficiency. In fact, this is one of the reasons black holes became so important in astronomy. Not because we can easily see the black hole itself, but because the disk around it can be so bright that it gives the hidden center away. In the case of giant black holes at galactic centers, this brightness can reach such extremes that we call the whole phenomenon a quasar. And quasars are not just bright in the casual way a street lamp is bright compared with a candle. They can outshine the galaxies around them. Just sit with that for a moment. A galaxy can hold hundreds of billions of stars. It is an enormous community of light spread across inconceivable distances. And yet, the central region around a feeding supermassive black hole can sometimes shine so intensely that it rivals or overwhelms the glow of all those stars combined. Not because the black hole is emitting light, but because matter on its way inward is being heated to almost unbelievable extremes. That may be one of the most poetic things in astrophysics. Darkness becomes visible through the suffering of light. And if that sounds dramatic, it is only because the underlying process really is dramatic. The matter in the disk is not resting. It is losing energy, spiraling inward, becoming ever more trapped. Orbit by orbit, it moves closer to the point of no return. The disk is, in a sense, a waiting room for disappearance. But before that disappearance, it becomes brilliant. The closer matter gets, the more fiercely it shines. It is almost as if the universe insists on one last burst of expression before the final silence. For a black hole like TUN 618, or any giant quasar-powered system, this disk is not a small accessory. It is the visible stage on which the whole cosmic drama plays out. Without the disk, the giant would remain mostly hidden. With the disk, it becomes one of the loudest gravitational statements in the universe. The remarkable thing is that the disk does more than simply glow. It also reveals character. This is easy to overlook. We tend to think of black holes as simple and identical, as if one black hole were just a larger or smaller version of another. But the region around a feeding black hole carries information. The brightness, the temperature, the spectrum of light, the behavior of the gas, the presence or absence of powerful jets, all of these give clues. They tell astronomers how fast the black hole is feeding, how energetic the system is, how matter is arranged, and perhaps even how the black hole has grown over time. So the accretion disk is not only beautiful, it is informative. It is one of the ways the hidden thing speaks. And the more extreme the black hole, the more dramatic this conversation becomes. Imagine, for a moment, standing far away from such a system, somewhere impossibly safe, somewhere where the radiation could never reach you with any real force. You would not see a neat disk in the way textbook diagrams often show it. Real astrophysical disks are too distant and too complex for that kind of clean visual simplicity. But conceptually, what you are looking at is a rotating structure of heated matter, an organized storm around an invisible center. A storm whose light can cross billions of light years. A storm so bright that it can announce the existence of a hidden dark object all the way across the observable universe. That is extraordinary not just because it is beautiful, but because it means some of the universe's most powerful structures do not reveal themselves directly. They reveal themselves through influence, through surrounding behavior, through the consequences they create. In that sense, a quasar is almost like the atmosphere of an unseen king. You do not see the ruler. You see what bends around the ruler, what glows in the ruler's presence, what survives, briefly, in the ruler's court. This is also where black holes stop being merely consumers and start becoming creators of cosmic change. Because a feeding black hole does not just affect the matter that crosses the event horizon. It affects the galaxy around it. The disk can radiate such vast energy that it changes the behavior of gas far beyond the immediate center. It can heat material. It can drive winds outward. It can disturb or even suppress the formation of new stars in the galaxy if enough energy is fed back into the surrounding environment. In other words, the black hole does not merely eat the galaxy from the center. It can regulate the conditions under which the galaxy lives. That is a stunning thought. A black hole, the ultimate symbol of inward pull, can also become an outward force through the energy generated by feeding. It can both swallow and influence. It can deepen the central darkness while simultaneously shaping the future of the stars around it. This is why astronomers often talk about black holes and galaxies as partners in evolution rather than separate objects with separate stories. The galaxy feeds the black hole with gas and matter. The black hole, when active, feeds energy back into the galaxy. One grows the other. One limits the other. One changes the future of the other. The relationship is not peaceful, but it is intimate. And in the case of extreme black holes, that relationship becomes even more dramatic. The brighter the feeding phase, the more powerful the surrounding effects can become. The giant black hole is no longer a hidden center tucked away in some unreachable darkness. It becomes a galactic event, a source of energy large enough to shape the history of whole star systems. There is something quietly humbling in that. Human life is so often framed by sunlight, by the warmth of a star, by the day-night rhythm that star makes possible, by biology built in its image. But elsewhere in the universe, whole galactic chapters may be shaped not mainly by stars, but by the feeding behavior of a black hole, by the light of material on its way to annihilation. Even the colors of that light, in a scientific sense, tell a story. Different parts of the disk can be hotter or cooler. Different regions emit different wavelengths. X-rays may come from the very hot inner environment. Optical and ultraviolet light may emerge from broader parts of the disk. Radio observations may reveal jets if the system launches them. The accretion disk is not just a glowing circle. It is a layered structure of energy, temperature, and motion. A changing map of the final journey inward. And yet, for all the violence implied by these words, there is also a strange serenity in the geometry of it. Orbit, friction, heat, light, spiral, disappearance. There is almost a ritual quality to the process. Matter enters the black hole's domain, loses itself into order, then turbulence, then heat, then radiation, then final loss. The whole thing unfolds according to the rules of gravity and motion, not morally, not emotionally, just physically. And there is something calming about that, if you let yourself feel it. Not because destruction is comforting, but because the universe is so consistent in the way it allows even its wildest events to happen through lawful processes. A black hole does not rage. It does not choose. It simply exerts gravity. The disk forms because motion and matter demand it. The heat appears because friction and compression make it unavoidable. The light appears because nature allows falling matter to become radiant before it vanishes. Even the most extreme black hole remains part of a coherent universe. Strange, yes. Terrifying at close range, certainly. But still intelligible. Still part of a larger order. This is one reason black holes feel different from ordinary fear. Fear is often about chaos, about losing the sense that anything makes sense. But the fascination of black holes comes from the opposite direction. They are so strange, and yet so structured, so extreme, and yet so rule-bound. They remind us that the universe can produce astonishing things without abandoning coherence. And perhaps that is why the image of the accretion disk stays in the mind so easily. It offers a perfect balance between mystery and explanation. You know what is happening, roughly. Matter is spiraling inward. But the scale, temperature, brightness, and implications are so vast that the understanding never becomes ordinary. The mind keeps slipping between clarity and awe, and that slipping can be strangely soothing. A gentle oscillation between what we know and what still feels impossible. If this slow descent into the heart of a black hole's luminous surroundings is helping you relax, this is a quiet moment to subscribe, like the channel, or leave a comment about which part of black holes fascinates you most. The darkness itself, the giant scale, the feeding process, the jets, or the strange fact that so much light can be born right next to a place where light ultimately cannot escape. There is another crucial detail here too. The disk does not last forever in the same way. Feeding phases come and go. Some black holes are quiet for long periods. Others flare into activity when enough matter reaches them. So when we observe a bright quasar, we may be catching a black hole in one specific phase of its life. A period of appetite. A period of high influence. A period of luminous unrest. That means every active black hole we study is also a kind of snapshot. A glimpse of one chapter, not the whole biography. That is part of what makes TUN 618 and other giant quasars so compelling. We are not just seeing a static object. We are seeing an episode. A giant in action. A hidden mass revealed through temporary brilliance. And since the light has taken so long to reach us, we are always seeing old action. Ancient chapters. Historical feeding. The universe arrives as memory. The accretion disk, then, is more than a structure. It is a message from the past. A bright record of what the black hole was doing when that light began its journey. And because the black hole itself remains hidden, the disk becomes the nearest thing we have to an autobiography written in radiation. It tells us the black hole was hungry. It tells us the environment was rich with matter. It tells us gravity was busy. It tells us the surrounding galaxy, or at least its central region, was not quiet. And perhaps most beautifully, it tells us that darkness is rarely alone. Even at the heart of one of the universe's most extreme objects, there is motion, heat, structure, consequence, and light. This brings us naturally to the next question. Because once you understand the disk of fire around the darkness, once you understand that black holes are not merely empty but active, not merely hidden but influential, another curiosity rises almost automatically. What would happen if something, or someone, actually went near one? Not just in the abstract sense of, it would be dangerous, because that much is obvious. But in the real physical sense, what would gravity do to time? To light? To the body? To the last possible orbits before the crossing? What would the approach to an extreme black hole actually feel like, at least as far as physics allows us to imagine? That is where the journey wants to go next. Because understanding a black hole from afar is one kind of wonder. Imagining what it would be like to fall toward one is another kind entirely. Part 6. If you went near an extreme black hole. There is a certain kind of question that appears almost automatically whenever people spend enough time thinking about black holes. Not the question of how they form. Not the question of how large they can grow. Not even the question of whether one can outshine a galaxy while remaining dark at its center. The question is more personal than that. What would actually happen if you went near one? It is a quiet, natural question, almost childlike in its honesty. The kind of question a person asks not because they plan to go, of course, but because imagination always wants one more step. It is not enough to know that a black hole is large, or bright around the edges, or powerful enough to shape a galaxy. At some point the mind wants to stand closer. It wants to picture the approach, the sky, the light, the body, the last orbit, the strange behavior of time, the final crossing. And black holes, perhaps more than any other object in the universe, reward that imagination with a mixture of beauty and unease. So let's approach slowly, not recklessly, not as a stunt, not like a science fiction hero diving toward danger with engines blazing, but gently, carefully, the way we have done everything else in this journey. Step by step, far enough away to remain calm, close enough to let the physics begin to speak. The first thing to understand is that going near a black hole does not describe just one situation. It depends enormously on the kind of black hole. A smaller black hole and a supermassive black hole are both black holes, yes, but the experience near them would be very different. This is one of those beautiful moments in science where instinct often gets the first guess wrong. People tend to imagine that the bigger black hole is automatically the more violently dangerous in every possible way. But in some respects, the opposite is true. A small stellar black hole has a much smaller event horizon. That means the gravitational gradient near it becomes extreme very quickly. In simple terms, gravity changes sharply over short distances. If your feet are a little closer to the black hole than your head, the difference in pull can become enormous. This is where the famous image of spaghettification comes from. The body is stretched lengthwise and compressed sideways by tidal forces. It is not a poetic term, but it is memorable because the image is so immediate. You become long, thin, pulled apart by gravity that does not treat every part of you equally. For a smaller black hole, that process could begin outside the event horizon. Long before you crossed the final boundary, the tidal forces would likely destroy you. But a supermassive black hole is different. This is one of the strangest truths in the whole subject. A black hole with vastly more mass has a much larger event horizon, and at that wider distance the tidal forces at the boundary can actually be gentler than those near a smaller black hole. Not gentle in the human sense, of course. Nothing about a black hole is truly gentle, but gentle relative to the alternative. It means that if you approached a truly supermassive black hole, the crossing of the event horizon itself might not feel like a sudden physical tearing, at least not immediately. And that alone is enough to make the imagination go quiet for a moment, because it means the most dramatic boundary in the universe, the line beyond which nothing returns, might in some cases feel strangely ordinary at the instant you crossed it. No flashing sign, no visible wall, no cosmic alarm, just one more moment of falling, while the outside universe silently lost the ability to receive any further message from you. That is worth sitting with. The event horizon is often spoken of as if it were a surface, like the skin of a sphere, but it is not a surface you could touch. It is a boundary in space-time, a threshold of escape. Outside it, there is still some path light can take outward. Inside it, there is not. That is all. Physics does not owe the traveler a theatrical effect at that boundary. The drama is not in what you feel at the exact crossing. The drama is in what the crossing means. Now imagine, if you can, that you are still safely outside, still approaching, still able to look around. What would you see? The answer is already strange before you get especially close. A black hole bends light. That is one of the most important things gravity does in extreme conditions. It curves space-time, and light follows that curvature. So the sky near a black hole would not look normal. Background stars would appear distorted. Light from behind the black hole could be bent around it, producing rings, arcs, warped images. The darkness at the center would not simply be a clean black circle pasted onto the sky. It would be surrounded by a region where the geometry of seeing itself begins to misbehave. This is one reason black holes are so visually haunting in simulation. They are not just dark. They are distorters. They turn the universe into something that looks almost familiar until you notice that the background has begun to curve, that the stars are no longer where they should be, that the ordinary rules of perspective have been replaced by the rules of deep gravity. And if the black hole is actively feeding, if it has a luminous accretion disk around it, then the scene becomes even more surreal. The disk would not appear simply as a flat band. Because light from the far side of the disk can be bent upward and around by gravity, you may see parts of the disk that ought to be hidden. The system begins to look doubled, layered, lifted above itself. An impossible halo of fire around a darkness that is also reshaping your view of the fire. There is something almost dreamlike about that image. A black center. A bent ring of blazing matter. The far side made visible by curvature. The near side distorted by speed, gravity, and light. It is no wonder black holes capture the imagination so easily. They are not just powerful. They are aesthetically strange. And yet the visual oddness is only the beginning. Because once you begin to approach an extreme black hole, time itself starts to behave in unsettling ways. This is one of the reasons black holes feel so philosophically powerful. They do not only threaten the body, they challenge ordinary intuition. According to general relativity, strong gravity affects the passage of time. The closer you are to a deep gravitational well, the more slowly your time passes relative to someone farther away. This is called gravitational time dilation. That phrase can sound technical, but the idea is wonderfully simple in its outline. Near a black hole, time runs differently. If someone watched you fall toward the black hole from a safe distance far away, their view of you would become increasingly strange. Your clock would appear to slow. Your signals would take longer to reach them. Light from you would become more redshifted, stretched to longer wavelengths as you approached the horizon. To the distant observer, you would seem to slow more and more, fading and reddening, never quite crossing the event horizon in any straightforward visible way. You would appear to freeze near the edge, dimmer and dimmer, quieter and quieter, until practical visibility gave out. But for you, the falling observer, the experience would be different. Your own clock would feel normal. Your heartbeat would not seem delayed. Your thoughts would arrive at their usual pace. You would not feel your personal time slowing. That is one of the deepest and most beautiful features of relativity. Each observer gets a reality that is locally consistent. The distance between these two experiences, yours and the distant observers, is not a contradiction. It is part of the geometry of spacetime itself. So in one sense, you fall through. In another sense, the outside universe never really watches you do so in a neat, complete way. This creates one of those wonderfully calm scientific paradoxes that black holes are full of. From far away, you seem to linger near the edge. From your own view, you continue inward. The two stories coexist because the universe at that depth does not obey the old easy intuitions of absolute time. And if you let your mind rest there for a moment, the emotional effect is almost meditative. Time, which feels so strict in ordinary life, becomes flexible near a black hole. The thing that rules our days, our deadlines, our aging, our sense of urgency, begins to loosen under gravity. Not because black holes are kind, of course, but because reality itself is stranger than our daily habits allow us to feel. Now let's imagine you are still outside the horizon of a supermassive black hole, perhaps one much larger than the black hole at the center of our galaxy, something approaching the giant class we have been discussing. You are falling inward. The sky behind you is bright with distorted stars. The disk around the black hole, if present, is a storm of light. Perhaps there are jets flung far outward from the poles. Perhaps there is intense radiation from the surrounding environment. That last part matters more than people often realize. In many realistic black hole scenarios, long before you reached the horizon, the environment itself would already be lethally hostile. An active quasar would flood its surroundings with radiation. Nearby infalling gas could be unimaginably hot. The accretion disk is not merely beautiful from a distance. It is dangerous up close. So when people imagine a smooth cinematic fall toward a black hole, physics often interrupts with an important correction. The environment might kill you well before the horizon became the main concern. But let us keep the thought experiment clean. Let us imagine, for the sake of understanding, a path that avoids the worst of the radiation and the disk. A calm enough route to focus on gravity itself. This is not how most real quasar environments would behave, but it allows the central ideas to become clearer. As you fall, one boundary of importance is the innermost stable circular orbit. Outside a black hole, there are possible orbits. Matter can circle. Stars can remain bound. Gas in the accretion disk can spiral inward gradually. But there comes a point where stable circular orbits are no longer possible. Inside that region, falling inward becomes unavoidable. Orbit is no longer a long-term negotiation with gravity. It becomes surrender. This is another reason black holes feel different from stars or planets. Around a planet, you can orbit quite peacefully if you are at the right speed and distance. Around a black hole, there is a final border beyond which that balance collapses. After that, there is no stable path that simply goes around forever. There is only inward. And that inwardness is total. This may be the most unsettling emotional feature of black holes. Not that they are destructive. Many things in the universe are destructive. Supernovae are destructive. Collisions are destructive. But black holes embody inevitability. Once you are sufficiently committed, once you cross certain boundaries, the future becomes strangely singular. There are no side roads, no outward curves, no escape route hidden in cleverness. Gravity writes the ending very clearly. And still, the experience of falling might be eerily calm at first, especially for a supermassive black hole. That is one of the themes science keeps returning to here. The deepest violence may not arrive with spectacle. It may arrive with silence. You might cross the horizon of a very large black hole without immediate drama in your body, only to find that all possible futures now point inward. The danger is not always in the sensation. Sometimes it is in the geometry. This makes black holes feel less like explosions and more like traps in the structure of reality. Now, if you continued inward, tidal forces would eventually grow stronger. Even for a supermassive black hole, the spaghettification problem does not disappear forever. It is merely postponed. Deeper inside, differences in gravity between one part of your body and another would become enormous. Stretching would intensify. No material object, human or otherwise, could survive indefinitely under such conditions. Somewhere further in, the body would lose its integrity. And beyond that lies the singularity, at least in the current classical picture. A place where general relativity predicts that density becomes effectively infinite and the equations themselves stop behaving in ways we know how to trust. That is an important scientific honesty point. We often speak of the singularity as if it were a clearly understood object at the center, but in reality it marks the place where our current theories can no longer give a complete physical description. It may be that quantum gravity, a theory we do not yet fully possess, changes the picture entirely. The singularity may not be the final literal truth of nature so much as a sign that our mathematics has reached its limit. That, too, is worth noticing. Even at the very heart of the black hole story, science remains humble. We know a great deal, but not everything. The edge of knowledge remains intact. There is another haunting thought experiment people sometimes ask about. Could you use a black hole to travel into the future? In a limited and very careful sense, the relationship between gravity and time means black holes highlight how future travel is already woven into relativity. If you spent time in a region where your clock ran more slowly relative to the outside universe, and then returned, more time could have passed for the outside world than for you. In that broad sense, strong gravity can create a difference in aging between observers. But the fantasy versions of black holes as convenient portals tend to outrun what the physics supports. Real black holes are not designed for comfort. They do not offer safe bridges by default. They offer extreme conditions, deep curvature, and a great many ways for ordinary matter to have a very bad day. Still, the association between black holes and time remains powerful for good reason. Near a black hole, time stops feeling like the simple straight river of everyday life. It becomes terrain. It bends. It stretches. It separates observers into different stories. That may be why black holes are never just astrophysical objects in the imagination. They become symbols of deeper things. Endings. Boundaries. Memory. Irreversibility. The hidden architecture of time itself. And yet, for all that philosophical weight, there is something very concrete and physical about the whole experience. Light bends. Clocks differ. Orbits fail. Tidal forces rise. Radiation burns. Matter spirals. These are not vague metaphors. They are the behavior of nature under extreme gravity. This is perhaps what makes the black hole journey so uniquely satisfying to think about. It feels like myth, but it is physics. It feels like dream imagery, but it is geometry. It feels like pure imagination, but the imagination is being guided by equations that describe the world astonishingly well. So, if you went near an extreme black hole, what would happen? You would first encounter distortion. The sky would bend. Light would misbehave. The environment might already be filled with lethal radiation if the black hole were active. Time, relative to faraway observers, would begin to separate from theirs. If you got close enough, stable escape would cease to be a practical option. For a supermassive black hole, the horizon itself might not feel instantly dramatic to your body, but it would be the most meaningful crossing imaginable. Deeper inside, tidal forces would eventually destroy any ordinary structure you brought with you. And at the center, our theories dissolve into uncertainty. That is the scientific answer. But there is also the emotional answer, and it is quieter. To go near a black hole is to go near a place where the universe stops pretending that ordinary intuition is enough. A place where light, time, and motion reveal their deeper rules. A place where reality becomes more honest than comfort allows. Black holes do not merely threaten us with destruction. They remind us that the world is built from principles deeper than habit. And perhaps, strangely, that is why people find them relaxing to think about at night. Not because they are safe. They are not. But because they are so far beyond the scale of ordinary life that they pull the mind out of its little loops. A black hole does not care about the day's embarrassments, the unfinished email, the missed train, the future meeting. It is too large a thought for that. It bends time. It reshapes light. It absorbs even urgency into perspective. If this journey toward the edge of gravity is helping you settle deeper into the night, this is a gentle moment to subscribe, like the video, or leave a comment about which part of black holes you find most fascinating. The strange visuals, the time dilation, the final boundary, or the idea that the biggest cosmic crossing might feel almost ordinary in the instant it happens. For now, though, one final thought lingers. Most of us will never go anywhere near a black hole, of course. We will know them only from afar, through telescopes, mathematics, simulations, and imagination. But that distance may be part of the gift. Because from far away, a black hole is not only a threat. It is a lens through which we can see gravity more clearly, time more clearly, and maybe even our own scale more clearly. And that prepares us for the next stage of the story. Because once you understand what it might be like to approach an extreme black hole, another question emerges naturally. Are we even sure which black hole deserves the title of most extreme in the first place? Is it always the biggest? Or could another black hole, faster spinning, earlier born, more violently feeding, or more dynamically strange, deserve that title just as much? That is where the mystery opens up again. Because the word extreme, as it turns out, is still not finished with us. Part 7. Is it really the most extreme ever found? By now, the question has become beautifully unstable. At the beginning, it sounded so simple. What is the most extreme black hole ever found? That phrasing feels clean. It feels as though the universe should be willing to hand us one winner, one clear champion, one final answer wrapped in a name and a number. Perhaps ton 618. Perhaps some newly discovered giant in the young universe. Perhaps the black hole that feeds too fast, or spins too quickly, or launches the longest jet. But the deeper you go into black holes, the more the question begins to loosen. It stops behaving like a tidy quiz and starts behaving like a doorway. Because most extreme is not one measurement. It is a collection of edges, a landscape of different kinds of excess. And once you see that clearly, something interesting happens. The search for one single winner becomes less satisfying than the larger truth. The universe does not seem particularly interested in giving us one final champion. It prefers categories. One black hole is extreme because it is unimaginably massive. Another because it seems to have formed much too early. Another because it feeds at a rate that unsettles the old limits. Another because its spin drags space-time into extraordinary behavior. Another because its jets cross distances that begin to feel more like architecture than motion. Another because it sits in the center of a galaxy and appears to have reshaped the fate of everything around it. And so the question of whether ton 618 is really the most extreme ever found becomes less about yes or no, and more about what exactly we mean when we ask. If we mean the heaviest known black hole, then it is one of the strongest candidates. That is the category in which its name appears most often. It sits near the top of the known scale so naturally that it has become, in a sense, a symbol for black hole enormity itself. If a person asks casually for the most extreme black hole, and what they really mean is the biggest one, then ton 618 is the answer most likely to satisfy. But mass is only one language of extremity, and black holes speak several. Take spin, for example. A black hole can be smaller than ton 618 and yet far more astonishing in the way it twists the space around it. Spin is not always the first thing people think of when they imagine a black hole, but in physics it matters tremendously. The faster a black hole spins, the more dramatically it affects its surrounding region. It changes how close matter can orbit before falling in. It affects how efficiently energy can be extracted from the environment. It may be deeply connected to the launching of powerful jets. In a sense, a rapidly spinning black hole is not merely heavy. It is dynamically intense. This matters because a black hole can be more extreme in one kind of behavior without being the largest overall. A smaller black hole with an astonishing spin may be more important for one branch of astrophysics than a giant but more ordinary feeder. It may reveal different physics. It may offer stronger clues about how black holes extract energy, how matter behaves close to the event horizon, or how magnetic fields organize under extreme conditions. So in that category, the title of most extreme may belong elsewhere. Then there is youth. This is perhaps one of the quietest and most unsettling categories of all. A black hole that already appears huge when the universe is still very young can be more shocking than a larger black hole found much later in cosmic history. Because scale alone is not the only problem. Timing matters. A black hole of moderate size in the nearby universe may not disturb theory very much. It has had an enormous amount of time to grow. But a black hole that appears very early, already hungry and already powerful, may be more disruptive even if it is less massive than Ton 618. That kind of extremity is chronological. It is not about how big the black hole is in isolation. It is about whether the universe should have been able to produce it so soon. And this, in some ways, is the most intellectually troubling kind of black hole. Not the one that is merely large, but the one that arrives before the script feels ready for it. These early giants force astronomers to revisit the opening chapters of the black hole story. They ask whether the seeds were bigger, whether the feeding phases were more intense, whether the early universe was a stranger nursery than we once assumed. In that sense, a black hole can be more extreme not because it wins the mass contest, but because it places more pressure on explanation. This is a useful way to think about extremity in science more generally. The most extreme object is not always the one with the most dramatic number. Sometimes it is the one that breaks the story most severely. The one that leaves theory least comfortable. The one that refuses the easy timeline. The one that forces a rewrite. And in black hole astronomy, those rule breakers matter enormously. There is also appetite. We talked earlier about the Eddington limit, that elegant balancing act between gravity pulling matter inward and radiation pressure pushing outward. In the standard picture, this limit acts like a regulator. It helps determine how quickly a black hole can grow in a steady way. But nature, as usual, appears to enjoy exceptions. Some black holes seem to feed above that limit, perhaps briefly, perhaps under specific conditions, perhaps more often in the early universe than we once realized. A black hole in one of these feeding frenzies may be more extreme, in a practical and physical sense, than a much heavier but quieter giant. Why? Because it is active in a more disruptive way. It is doing something now, or at least in the observed moment of its ancient light, that stretches our models. It is eating too quickly, shining too intensely, and potentially growing at a rate that changes how we think cosmic giants are built. In that category, most extreme points less toward total accumulated mass and more toward present behavior. That distinction matters. Ton 618 may be the heavyweight, but another black hole, caught in the act of super-Eddington feeding, may be the more dramatic character in that moment, the more revealing object, the one telling us something more urgent about black hole growth. And then, of course, there are jets. A black hole launching a long, narrow, near light-speed jet across intergalactic distances is extreme in a way that almost escapes ordinary language. The black hole is not merely consuming. It is participating in large-scale cosmic design. It is throwing energy back into the universe in ways that can shape the gas around galaxies, heat the medium between them, and announce its presence over distances that dwarf any human intuition. If you think of mass as silent authority, then jets are declaration. A black hole with astonishing jets may not be the heaviest known, but it may be one of the most dynamically forceful. It may change its surroundings more aggressively. It may become visible across much larger scales through its influence. In that sense, some black holes are extreme not as objects, but as events. Their significance lies in how far their energy reaches. And that is a beautiful distinction too, because it reminds us that the black hole itself is only one part of the story. The surrounding effects matter. The galaxy matters. The environment matters. A black hole that shapes its host system dramatically may deserve the word extreme even if another black hole outweighs it by some enormous factor. There is something almost human about this. Not in emotion, of course, but in interpretation. We are always trying to decide what should count most. Raw size? Timing? Influence? Activity? Strangeness? We do the same thing in every other realm of life too. Is the most powerful person the richest one, the fastest one, the loudest one, the earliest one, or the one who changes the most around them? Black holes quietly ask the same question. And the answer depends on what kind of astonishment you value. If you value scale, ton 618 remains difficult to beat. It feels like the cleanest answer to the original question in its most popular form. A black hole so massive that the phrase supermassive begins to feel undersized. A giant whose name has become almost synonymous with black hole excess. But if you value violation of expectation, then some younger, faster feeding, earlier appearing, or more violently active black holes may feel even more extreme. Because they do not merely sit at the end of a scale. They interfere with the story itself. There is another reason this matters, and it may be the most scientific reason of all. Science does not really care about winners in the way sports do. Science cares about what nature is trying to tell us. A black hole becomes important not merely because it is the largest or brightest, but because it teaches something. Because it clarifies a mechanism. Because it reveals a gap in understanding. Because it forces old theory to widen. Because it helps make sense of the larger population. So when we ask, is ton 618 really the most extreme ever found, we are also asking what kind of knowledge we want from a black hole. Do we want a monument? Or do we want a clue? Ton 618 is certainly a monument. It stands there in the imagination like a mountain of gravity. A kind of upper edge symbol. It is the black hole people point to when they want the feeling of immensity. And there is value in that. Human thought needs symbols. We need names that hold scale for us, names we can come back to when reality becomes too abstract. Ton 618 performs that role beautifully. It is the kind of object that helps the mind feel the upper atmosphere of black hole possibility. But the clue objects matter just as much, perhaps more. A black hole that appears too early. A black hole that grows too fast. A black hole that shines in a combination of wavelengths we did not expect. A black hole that launches jets while apparently feeding in a way that should have disrupted them. A black hole that lives in the awkward gap between categories, showing us that the categories themselves were too neat. These are the black holes that make science move. And perhaps that is why the answer to the original question can never be fully final. Because the sky is not done surprising us. New surveys continue. Better telescopes arrive. Deeper observations refine estimates. Objects once thought to be record holders may someday be surpassed, or reinterpreted, or joined by stranger discoveries. That is not a weakness of astronomy. It is its rhythm. The universe is not a list we finish. It is a conversation we keep entering more deeply. There is a calm kind of beauty in that, especially at night. Especially when the mind is tired of tidy answers and just wants something large enough to rest inside. Black holes give us that. Not certainty, exactly, but meaningful uncertainty. A well-structured unknown. A mystery with equations around the edges and silence in the center. And so perhaps the most honest answer to the question is this. TON 618 is very likely one of the best answers if by most extreme you mean the most massive black hole commonly cited in that category. It is the giant, the heavyweight, the black hole that most naturally carries the title when the imagination wants one overwhelming champion. But if most extreme means the earliest, the fastest growing, the most rapidly spinning, the most dynamically disruptive, or the most theoretically inconvenient, then the title becomes shared. Divided across a family of dark wonders, each one occupying its own edge of the map. And that, in the end, may be a more satisfying reality than a single winner would have been. Because it means the universe is not repetitive. It means black holes are not all competing in one race. It means extremity itself is richer than one measure. More textured, more intelligent, more interesting. It means that reality has not built just one kind of impossible object. It has built many. There is something deeply soothing about that idea. Not because it simplifies the cosmos, but because it allows it to remain abundant. One giant, one spinner, one glutton, one early arrival. one jet maker, one rule breaker, one silent heavyweight in the dark, each black hole carrying a different version of extremity, each one stretching our sense of what gravity can become, each one reminding us that the universe does not reach its limits in only one way. If this long drift through cosmic scale is helping you wind down, this is a soft place to like the video, subscribe to the channel, and leave a comment with your own answer. Which kind of extreme feels most fascinating to you? The biggest black hole, the earliest black hole, the fastest feeding black hole, or the strangest black hole in terms of behavior? It is always wonderful to see which edge of the mystery speaks most strongly to different people. For now, though, the question is beginning to widen one last time. Because once you stop asking which black hole deserves the crown, another thought appears. A quieter thought. A more reflective one. What do all of these extremes actually teach us? Not just about black holes themselves, but about the universe. About galaxy growth. About gravity. About time. About the early cosmos. About the strange fact that the darkest objects can become some of the brightest engines in existence. That, perhaps, is the gentlest and deepest ending to this journey. Not choosing a winner, but listening to what the extremes are trying to say. And that is where the story wants to go next. Toward the larger meaning hidden inside these giants. Toward what the most extreme black holes reveal about reality itself. Part 8, What the most extreme black holes teach us about the universe. After all the questions of size, hunger, spin, light, and danger, something softer begins to emerge. The most extreme black holes do not only impress us, they instruct us. That may be the quietest truth in this whole journey. We begin with spectacle because spectacle is easy to notice. A black hole tens of billions of times the mass of the sun, a quasar bright enough to challenge the glow of a galaxy, a feeding rate that seems to mock the usual limits, a jet launched across distances so large they almost stop feeling like motion and start feeling like structure. These things capture the imagination immediately. They deserve to. They are astonishing. But once the first wave of astonishment passes, another kind of question appears. A calmer one. A deeper one. What are these giant black holes actually telling us? What do they reveal about the universe that smaller, quieter, more ordinary objects cannot? And the answer, gently unfolding beneath all the extremity, is that black holes this large are not just cosmic curiosities. They are witnesses. They are records. They are clues left behind by the deepest processes in the universe. To study the most extreme black holes is to study the architecture of cosmic history itself. One of the first things they teach us is that the universe grew up faster and stranger than our simplest stories once suggested. This is one of the reasons early giant black holes are so scientifically valuable. They appear in the young universe already carrying enormous mass, already active, already central to luminous systems we can see across vast distances. And that means the early cosmos was not a quiet waiting room. It was not a blank, gentle nursery slowly preparing the conditions for complexity. It was dynamic, aggressive, structurally ambitious. The ingredients of galaxies, stars, gas flows, and black holes were interacting in ways intense enough to produce giants surprisingly early. That changes the emotional feel of the early universe. It is easy to think of the beginning of cosmic history as a softer, simpler place. Younger, yes, but in some calm and unfinished sense. Yet the most extreme black holes hint at something more restless. A universe that was already capable of dramatic concentration. Already capable of building deep gravitational centers. Already capable of channeling matter inward with startling efficiency. In that sense, the giants teach us that the early universe was not merely young, it was productive. And that matters because it reframes the whole story of cosmic evolution. Instead of imagining structure emerging slowly and politely, we begin to picture an environment where some processes moved with surprising force. Galaxies did not simply appear and then much later develop interesting centers. In many cases, the centers may have been important from very early on. The black hole was not always the afterthought. It may have been part of the opening act. This leads naturally to a second lesson. Extreme black holes teach us that galaxies and black holes do not live separate lives. This may sound obvious now, but it was not always treated with the same emphasis. There was a time when one could imagine a galaxy as the main story and the central black hole as a kind of strange add-on. A dark object in the middle, certainly interesting, but still secondary to the stars, dust lanes, and visible beauty of the larger galactic system. That view no longer feels sufficient. The most extreme black holes make it difficult to think that way. When a central black hole can outshine a galaxy in a quasar phase, regulate gas through energy feedback, shape star formation, launch jets, and influence the thermal history of its environment, it becomes very hard to treat it as a side character. It begins to look more like one of the authors of galactic fate. That is a very beautiful shift in perspective. A galaxy is not just a collection of stars with a passive dark center. It can be a conversation between stars and the black hole that lives among them. Matter falls inward. Energy comes outward. Gas cools, gathers, is heated again, is blown outward, returns, or is lost. The stars and the black hole become bound not only by gravity, but by shared history. One changes the conditions of the other. In this sense, the giant black holes teach us something very broad about the universe. They teach us that visible things are not always the whole story. The most influential actor in a system may be the one you cannot see directly. A galaxy may appear to be a city of stars, but the hidden darkness at the center can still help decide what sort of city it becomes. There is almost a philosophical comfort in that. Not because it is easy, but because it reminds us that the universe is layered. Surface brightness is not the same as causal importance. The visible is not always the decisive. Sometimes the center of power is dark. A third lesson emerges from the question of growth itself. How do you build something like Ton 618? That question leads not only to black hole physics, but to a larger truth about the universe. It tells us that nature is comfortable operating across timescales far beyond the ones that shape ordinary human feeling. Giant black holes are what happen when gravity is allowed to remain patient. When matter is allowed to keep falling inward, age after age, merger after merger, feeding episode after feeding episode. They are accumulations. Time made visible through mass. This is one of the reasons black holes so easily pull the mind into a calmer scale. They remind us that reality is not built mainly at the speed of human urgency. The deepest structures in the cosmos are formed by persistence, not by panic, not by immediacy, not by the emotional rhythm of a single lifetime, but by patient processes unfolding over millions and billions of years. A giant black hole is, in that sense, a monument to duration. It tells us that the universe remembers, not with memory in the biological sense, of course, but in the structural sense. Its past remains written into its present. A black hole's mass is a record of what it has been given, what it has kept, what it has survived. When astronomers weigh an extreme black hole, they are not only measuring an object, they are reading history. Condensed history, hidden history, gravitational history, but history nonetheless. And perhaps that is why these objects feel so much larger than the numbers attached to them. A billion or 10 billion or 60 billion solar masses is not only a large number. It is a compressed biography, a summary written in gravity. The most extreme black holes also teach us something humbling about the limits of theory. This may be one of their most important gifts. Science, at its best, does not merely celebrate what it has already explained. It listens for trouble. It notices where the world refuses the neat version. It pays attention when a new observation does not fit comfortably into the old scheme. And black holes, especially the extreme ones, are excellent producers of this kind of productive discomfort. A black hole that appears too early asks whether our seed models are too simple. A black hole that grows too fast asks whether our feeding limits were too strict or too narrow in their assumptions. A black hole that combines strange brightness, strong jets, and unusual environmental conditions asks whether the tidy categories in our simulations are missing real complexity. A black hole that bends time and light so dramatically near its horizon reminds us that even our most ordinary intuitions about space and duration are local conveniences, not universal truths. In that way, extreme black holes function almost like stress tests for human understanding. They are places where theory is asked to carry more weight. Sometimes theory succeeds beautifully. Sometimes it bends. Sometimes it needs repair. That is not a sign of failure. It is the normal, healthy rhythm of science meeting a universe more inventive than prediction. There is something peaceful about that too. Many people imagine science as the gradual elimination of mystery. But the deeper reality is gentler than that. Science often transforms mystery rather than erases it. It takes a vague wonder and replaces it with a more precise wonder. It removes confusion only to reveal a more interesting question underneath. Extreme black holes are perfect examples of this. We used to wonder if black holes existed at all. Then we wondered how they fed. Then how they grew so quickly. Then how they launched jets. Then how they shaped galaxies. Then how their environments behaved near the horizon. Then how quantum gravity might change the picture inside. The mystery does not die. It deepens. And that is perhaps one of the greatest things these black holes teach us. The universe is not only understandable, it is recursively understandable. Every answer opens into a better question. Another lesson arrives through the strange relationship between darkness and light. This is one of the quiet emotional cores of black hole science. A black hole is defined by darkness, by the inability of light to escape once it passes the horizon. And yet the most extreme black holes become known to us largely through light, through the radiation of accretion disks, through the brilliance of quasars, through X-rays, radio waves, and distorted optical signatures, through the glowing struggle of matter not yet fully lost. There is something profoundly elegant in that. The darkness reveals itself through what it changes. It is almost never the object alone that teaches us. It is the relationship between the object and its surroundings. The disk of fire around the hidden center, the bent light, the hot corona, the jets, the altered galaxy, the deep gravitational influence on everything nearby. We know the black hole by its consequences. This is not just a technical detail. It is a larger pattern in science and perhaps in life too. The most important things are often not seen directly. They are inferred through effect, known by what bends around them, known by what they make possible or impossible, known by the structure of the world they create. Black holes teach that lesson with exceptional clarity. And then there is time. No journey through black holes feels complete without returning to that word. Extreme black holes teach us that time is not the simple, uniform background it often feels like in daily life. Near these objects, time stretches. Clocks separate. Different observers no longer share the same easy story. The black hole becomes not only a region of intense gravity, but a place where the normal emotional certainty of time begins to soften. Minutes and years stop being as universal as they felt on Earth. This matters because it means black holes are not just about gravity in the narrow sense. They are about the structure of reality. They are about space-time itself. They are reminders that what feels ordinary to human life is not necessarily fundamental. The deeper rules of the universe can produce situations in which the familiar categories of before and after, near and far, visible and hidden, become far more subtle than intuition prepared us for. That realization can be unsettling, yes, but it can also be deeply calming. Because once you see how flexible reality becomes under the right conditions, The old confidence of the everyday world begins to loosen in a healthy way. It becomes easier to accept that your own perspective is local. Useful, yes. Real within its scale, yes. But not the final shape of truth. Extreme black holes teach humility not through moral instruction, but through geometry. They also teach scale in a more emotional sense. This may be the most quietly restorative lesson of all. Human beings live in a narrow band of size, time, and urgency. Our days feel full because they are. Our minds fill with tasks, fears, hopes, deadlines, memories, the ordinary weight of being alive in a small body with a short life. None of that is trivial. But then the mind turns toward a black hole billions of times the mass of the sun, seen in ancient light from across cosmic distance, and something relaxes. Not because our own concerns are fake, but because they are no longer the only available scale. The universe, through these black holes, gives us a larger room to breathe in. A room where gravity can take millions of years to shape a story. Where light can travel for billions of years carrying evidence toward us. Where galaxies and black holes can co-evolve in slow dramas too vast for a single mind to hold all at once. In that room, urgency becomes less absolute. The self becomes less cramped. Perspective returns. Perhaps this is one hidden reason people love black holes so much. They are not merely frightening objects. They are perspective machines. They take the mind beyond the local weather of its worries. And finally, the most extreme black holes teach us something about beauty. Not beauty in the decorative sense. Not beauty as comfort or softness. But beauty as coherence at the edge of comprehension. Beauty as the presence of structure where chaos seemed likely. Beauty as the fact that even the darkest and most violent corners of the cosmos still obey patterns we can slowly learn. A black hole does not become beautiful because it is harmless. It becomes beautiful because it is intelligible without becoming ordinary. It preserves mystery without collapsing into nonsense. It allows science and awe to coexist. That is a rare kind of beauty. A very deep kind. The kind that does not ask to be possessed or reduced, only witnessed. The kind that makes a person quieter, not louder. If this long, slow exploration is helping you drift deeper into rest, this is a gentle place to subscribe, like the video, or leave a comment about which lesson from black holes stays with you most. Their connection to time, to galaxy growth, to the early universe, or simply the strange fact that darkness can become visible through its influence on light. For now, though, as this chapter settles, perhaps the simplest ending is the most honest one. The most extreme black holes teach us that the universe is not casual about its greatness. It builds slowly, or suddenly, but always lawfully. It hides power in darkness. It lets light reveal what cannot shine. It binds galaxies to invisible centers. It stretches time without breaking reality. It produces objects so large and strange that human intuition fails, and then invites human curiosity to keep going anyway. And maybe that is the deepest lesson of all. That the universe is not obliged to match the scale of our understanding before we begin. We are allowed to approach slowly. Allowed to wonder imperfectly. Allowed to keep learning in the presence of things far greater than ourselves. The giant black holes do not demand that we conquer the mystery, only that we remain awake to it. And that is a very peaceful place to end. Because once you have listened long enough to the most extreme black holes, one final feeling begins to remain after all the science. Not fear, not even astonishment, exactly, but a kind of quiet gratitude for living in a universe strange enough to contain them. Part 9, the place where physics still goes quiet. After everything we have explored so far, a strange thing begins to happen. The black hole stops feeling like a destination. It starts feeling like a boundary. At first, that may sound like the same idea, but it is not. A destination is a place you reach, understand, and then describe. A boundary is a place where your description begins to fail. A place where your ordinary tools still work for a while, then work less well, then suddenly go quiet. And that may be one of the most important things the most extreme black holes teach us. Not just that gravity can become overwhelming, not just that galaxies can grow around hidden centers, not just that time and light behave strangely near deep spacetime wells, but that even our best science has edges. And black holes live very close to those edges. This is one of the reasons they have remained so compelling for so long. Not only because they are dramatic, but because they occupy the place where successful physics and unfinished physics meet. The equations of general relativity describe black holes astonishingly well in many respects. They help us understand the event horizon, orbital behavior, time dilation, accretion, gravitational lensing, and much more. But the deeper you go into the heart of a black hole, the more the old confidence begins to soften. Eventually, the mathematics itself begins to tell us something humbling. You have come as far as I can take you. That is a beautiful sentence when it belongs to a person. It is a troubling sentence when it belongs to a theory. And yet that is exactly what happens near the innermost depths of black hole physics. The name usually given to that problem is the singularity. It is one of those words that sounds powerful enough to end the discussion, and yet really it begins a new one. In the familiar description, a singularity is the point at the center of a black hole where density becomes effectively infinite and spacetime curvature becomes extreme beyond the ability of our current equations to handle in an ordinary way. It is often described as though it were a final object, a literal point of ultimate compression. But a more careful way to say it is this: the singularity is where our present mathematical description stops being trustworthy. That is an important difference, because when people first hear about singularities, they often imagine science confidently announcing that the center of a black hole is an infinitely dense point and that this is the end of the story. But science is actually more modest than that. What it says is closer to this. If we use general relativity alone, and follow the equations inward, the result we get is a singularity. This may mean there really is something like that there. Or it may mean that general relativity, magnificent as it is being pushed beyond the domain where it can give the whole truth. And that is not a defeat. It is a clue that some deeper theory is waiting beyond it. This is where the story of black holes becomes especially beautiful, because they do not merely confirm what we know. They expose where knowledge must grow. They are not only cosmic objects. They are tests. They force physics to stand in a difficult place and explain more than it has yet learned to explain. To understand why this matters so much, it helps to remember that modern physics rests on two great pillars. One is general relativity, which describes gravity, space-time, and the large-scale structure of the universe with extraordinary success. The other is quantum mechanics, which describes the small-scale behavior of matter and energy with equally extraordinary success. Both theories are brilliant. Both are deeply confirmed in their own domains. But they are not yet fully united. And black holes are one of the places where that lack of unity becomes impossible to ignore. Because a black hole is both very large and, in some sense, driven toward the very small. It is a place where gravity becomes dominant on a huge scale, and where matter is driven toward conditions so extreme that quantum effects should eventually matter too. General relativity alone takes us very far. Quantum mechanics explains a great deal about the microscopic world. But at the center of a black hole, or in the earliest moment of the Big Bang, we seem to need both together. We need a theory of quantum gravity. And we do not yet have a finished one. This is one reason black holes are not only interesting to astronomers. They are also sacred ground, in a sense, to theoretical physics. Not sacred in a religious way, of course, but in the way difficult things become sacred to thought. They are places where the universe is clearly telling us that our work is not done. And perhaps that is why the extreme black holes feel so different from ordinary large objects. A mountain is large, but it does not challenge the foundations of physics. A star is powerful, but it remains mostly within the language we already know how to speak. A black hole, especially an extreme one, is different. It is not merely a giant thing. It is a giant question. This becomes even more striking when we move from the center of the black hole to the boundary around it, the event horizon. You might think the event horizon would simplify the story. After all, it gives us a clean line, a threshold, a place that seems easy to define. Outside, escape is still possible. Inside, it is not. That sounds neat, perhaps even comforting in its clarity. But black holes, again, are rarely content with only one layer of mystery. Because once physicists began thinking carefully about quantum effects near black holes, another astonishing problem emerged: the problem of black hole evaporation. This idea is associated with Stephen Hawking, and it remains one of the most extraordinary insights in 20th century physics. In simple terms, black holes are not completely black when quantum mechanics is taken into account. Over incredibly long timescales, they can emit radiation, now called Hawking radiation, and gradually lose mass. Very slowly, unimaginably slowly for large black holes, they can evaporate. This alone is enough to feel surreal. A black hole, the very emblem of inescapability, is not entirely final in the way people once imagined. Even it has a future. Even it changes. But Hawking radiation leads to a much deeper problem. What happens to information? This may sound technical at first, but the emotional shape of the question is wonderfully simple. If something falls into a black hole, what becomes of the details that defined it? Not just its mass, not just its charge, not just its general contribution to the black hole's properties, but the full subtle information about what it was. In ordinary quantum mechanics, information is not supposed to vanish. The world changes, yes, but in ways that preserve underlying information. Yet black holes seem to threaten that principle. If matter falls in, and the black hole later evaporates through Hawking radiation that looks mostly random, then it begins to seem as though information has been lost from the universe. That would be a profound problem, because it would place black holes in tension with the basic logic of quantum theory. This became known as the black hole information paradox. And once again, what black holes offer us is not comfort, but depth. They force two successful ways of describing reality to meet in a place where they do not easily agree. General relativity says one thing about horizons and collapse. Quantum mechanics says another thing about information. And the black hole sits there in the middle, not apologizing, just existing, while physics works to become larger. That may be one of the most intellectually beautiful things in all of science. Nature does not arrange itself to spare us difficulty. It simply is what it is. And then it lets us grow to meet it. Over the years, many ideas have been proposed about the information paradox. Some suggest that information is somehow encoded in subtle ways in the outgoing radiation. Some suggest that the event horizon may not behave exactly the way earlier intuitions imagined. Some ideas involve holographic principles, strange relations between gravity and lower dimensional descriptions of reality, almost as if the universe were whispering that space itself may have a deeper informational structure than we guessed. Now, for a sleep-style science journey like this, there is no need to drag ourselves through the full technical forest of those arguments. The deeper point is gentler and simpler. The most extreme black holes show us that reality may be more informationally subtle than our ordinary picture suggests. They hint that space, matter, light, and even the idea of what is preserved in the universe may belong to a deeper order still being uncovered. In other words, black holes are not only places where things end. They are places where physics begins again. And then there is the horizon from another angle, the human angle. We often speak of black holes with a kind of finality. The point of no return. The ultimate trap. The place where all futures point inward. And that is true in one important sense. But from the perspective of theory, black holes are also places where certainty thins. That makes them emotionally unusual. They feel like endings in the physical imagination and beginnings in the intellectual one. A black hole is where the traveler's path seems to close, but it is where the theorist's path opens. That is a rare combination, and perhaps that is why the subject remains so strangely alive. There is always one more layer to ask about, one more silence in the equations, one more possibility hiding just beyond the reach of the present model. This is also where extreme black holes differ from the more ordinary black holes we might imagine from stellar collapse alone. A black hole like Ton 618 is so enormous, so deeply woven into cosmic history, that it does not only raise questions about horizons and singularities, it also raises questions about growth, feedback, structure formation, and the behavior of matter under extreme conditions across immense scales. In other words, the giant black holes do not live near just one boundary of knowledge. They live near several. They are boundaries between galaxy evolution and black hole growth, between luminous matter and hidden mass, between relativity and quantum uncertainty, between what can be observed directly and what must be inferred through light and consequence, between the known and the not yet known. This is worth pausing on, because by now, the most extreme black holes have become more than objects in the story. They have become mirrors for the limits of explanation. They reveal what science can do magnificently, and where science must still proceed with humility. They show us that understanding is not a single achievement. It is a layered landscape. Some hills have been climbed, others are still far away. Some clouds have been entered, but not yet crossed. And if you let yourself feel that properly, it is not frustrating. It is peaceful. There is a strange peace in realizing that even the most disciplined human inquiry still lives inside a larger mystery. Not a vague mystery, not an excuse for abandoning thought, but a disciplined mystery. A mystery with equations, observations, telescopes, simulations, and lively debate. A mystery that narrows and deepens as understanding grows. Black holes give us that kind of mystery in perhaps its purest modern form. They are not magical because they are unexplained. They are beautiful because they are partly explained and still deep. That may be one of the reasons people never tire of them. A completely unknown thing can feel empty. A completely known thing can begin to feel ordinary. But a black hole lives in that exquisite middle region where knowledge is real and incomplete at once. Enough to hold the mind. Enough to keep it open. This has consequences beyond black holes too. The work done to understand these objects influences many parts of physics. Ideas about information, entropy, quantum fields, gravity, and spacetime all become sharper in the presence of black holes. They act like intellectual furnaces. Problems thrown into them do not vanish politely. They come back transformed, more difficult perhaps, but also more revealing. There is something almost appropriate about that. A black hole consumes matter and returns puzzles. And in the same way that matter around a black hole glows before crossing the horizon, human thought glows when forced close to the edge of what it cannot yet fully master. If this quiet descent into the unanswered heart of black hole physics is helping you settle deeper into rest, this is a gentle place to like the video, subscribe to the channel, or leave a comment about which mystery fascinates you most. The singularity, Hawking radiation, the information paradox, or the simple haunting fact that even our best theories eventually fall silent somewhere. For now, though, there is one more emotional movement left in the story. Because once you see black holes as places where physics still goes quiet, something softens in the way you think about them. They stop being merely cosmic threats. They stop being only giant gravitational machines. They become something else. They become reminders. Reminders that reality is larger than any one framework. That some of the greatest scientific achievements in history are still chapters, not the whole book. That the universe does not reveal itself all at once. That our species, brief and local as it is, has nonetheless learned to ask questions brave enough to reach the edge of space-time and listen there. And perhaps that is the deepest calm hidden inside all this darkness. We do not need the mystery to be finished in order to live meaningfully beside it. We do not need black holes to become fully ordinary before they become beautiful. We do not need every silence in the equations to be filled before the universe becomes worthy of love. Sometimes it is enough to know that the edge exists, enough to know that thought can reach it, enough to know that beyond the last clean line of present understanding, the cosmos is still there, waiting. And that prepares us for the final part of the journey. Because after all the giants, the light, the growth, the danger, the categories, the unanswered questions, there is one final place to arrive. A quieter place. A place where the story is no longer mainly about black holes, but about us, looking at them. About what it means to be a small consciousness in a universe large enough to contain such things. About why these dark objects, so far away and so unlivable, can still bring a strange kind of peace. That is where we go next. Not deeper into the black hole, but deeper into the feeling it leaves behind. Part 10. Why the darkest things can still bring peace. By the time we arrive here, the question we started with has changed almost completely. At first, it seemed like a question about an object. What is the most extreme black hole ever found? That was the doorway. A good doorway. Clear, direct, easy to picture. It gave us something to follow into the dark. But along the way, the question became larger than its own wording. It stopped being only about which black hole holds the most dramatic title, and started becoming a question about what these objects do to the human mind once we really sit with them. Because after enough time spent with black holes, especially the most extreme ones, something unexpected begins to happen. They stop feeling like cosmic monsters, and they begin to feel like perspective. That may sound strange at first. Black holes are dangerous, violent, unlivable. They distort light, bend time, destroy matter, power quasars, and sit at the edge of what our best physics can explain. There is nothing soft about them in the ordinary sense. Nothing cozy. Nothing safe. And yet, people come back to them again and again, especially at night, especially in quiet moments, especially when the mind is tired and wants something larger than itself to rest against. There must be a reason for that. And perhaps the reason is not that black holes are comforting in themselves, but that they rearrange the scale on which comfort becomes possible. A human day is made of very small weather. Messages, plans, deadlines, unfinished thoughts, little embarrassments, the quiet friction of trying to be a person in the world. None of those things are trivial. They are part of life. But they are local. Very local. And the mind, when it stays inside only that local scale for too long, can begin to feel cramped. Every problem becomes the size of the room. Every worry becomes the size of the night. Then a thought enters. A real one. A scientific one. A black hole tens of billions of times the mass of the sun, wrapped in ancient light, known through a quasar so bright it can challenge the glow of a galaxy. Suddenly the room is not the only scale available anymore. This is what black holes do so well. They interrupt claustrophobia. They do not solve our human problems directly. That would be too simple, and not really true. But they do something more subtle. They remind the mind that reality is wider than urgency. They create space around thought. They loosen the emotional grip of the immediate by making available a larger frame, a deeper background, a calmer horizon. And maybe that is why the darkest objects in the universe can still bring peace. Not because they are gentle, but because they are vast enough to make gentleness possible in us. When we first spoke about extreme black holes, we looked for records. The largest one, the earliest one, the fastest feeding one, the one that spins hardest, launches the most dramatic jets, or pressures theory into new shapes. And all of that matters. It matters scientifically, and it matters imaginatively too. Human beings are drawn to edges. We like to know how far nature can go. We like to know the upper limits, the strangest cases, the things that make ordinary categories fail. But if there is one thing the most extreme black holes have shown us, it is that reality does not reach its limits in only one way. One black hole becomes extreme by mass, another by youth, another by appetite, another by spin, another by influence on the galaxy around it, another by the way it troubles theory, by the way it makes equations hesitate, by the way it forces science to admit that its present language, however beautiful, is not yet complete. That is a lovely thing to realize, because it means the universe is not built around one kind of greatness. It means there is no single way to become astonishing. Even among black holes, the forms of extremity are many, and perhaps there is something quietly healing in that too. We spend so much of life being told, in one way or another, that there is one proper scale, one correct pace, one acceptable shape of success, one winner, one clearest answer. But the universe is often less rigid than that. It makes room for multiple edges, multiple forms of excess, multiple ways for something to matter. A giant like Ton 618 matters because it is so staggeringly massive that it stretches the imagination. The early giants matter because they force us to rethink the timeline of cosmic growth. The violent feeders matter because they show us that the universe sometimes grows its monsters in bursts, not only in long, slow patience. The horizon matters because it reveals the strange flexibility of time. The singularity matters because it marks the place where even brilliant theories must grow quiet. And all of it matters because it shows us that black holes are not just objects in space. They are crossings between many kinds of understanding, between gravity and light, between galaxies and their hidden centers, between what can be seen and what must be inferred, between the known and the not yet known, between fear and wonder. There is something deeply calming about a mystery that is this well-shaped. Not a vague mystery, not a lazy unknown, but a disciplined mystery. One that holds still long enough for us to study it. One that responds to mathematics, to telescopes, to careful patience, to better instruments, to better ideas. A mystery that does not vanish under investigation, but becomes richer. That is one of the great gifts of black holes. They allow science and wonder to inhabit the same place without weakening each other. The more we learn, the more astonishing they become. The more astonishing they become, the more meaningful learning feels. That is a rare balance. And perhaps it explains why black holes linger so well in the mind. They do not flatten into ordinary knowledge once explained. They remain alive. Not because science has failed, but because science has succeeded just enough to reveal deeper structure beneath the first layer. You can understand that a black hole bends light and still be moved by the image of a warped sky. You can understand gravitational time dilation and still feel the quiet shock of realizing that time is not the same story everywhere. You can understand accretion disks and still be affected by the poetry of darkness revealing itself through surrounding light. You can understand the information paradox in outline and still feel the breathtaking fact that the universe contains places where two of our best theories still do not fully meet. This is not a weakness of understanding. It is one of its highest forms. The ability to know something truly and still remain open to its depth. That may be one of the most restful emotional states a person can enter. To stop trying to reduce reality into something small enough to own, and instead let it stay large while still feeling held by the fact that some part of it can be understood. Black holes invite that state beautifully. They are too large to master in one thought, and yet structured enough to contemplate without despair. And because of that, they create a kind of peaceful humility. Humility is often misunderstood as thinking less of oneself. But the best humility is not self-erasure. It is accurate scale. It is the relief of no longer needing your local viewpoint to be the whole stage on which reality performs. Extreme black holes offer that relief. They remind us that we are small, yes, but not in a humiliating way. in a clarifying way, in a freeing way. We are small enough to wonder, small enough to learn, small enough to be surprised, small enough that the universe can still exceed us without making us irrelevant. That last part matters, because there is a temptation, when confronted with cosmic scale, to slip into a kind of emotional defeat. To say that if the universe is this large and we are this small, then nothing we do matters. But black holes do not really teach that. Not if you stay with them long enough. What they teach instead is more nuanced, and much kinder. They teach that scale and meaning are not enemies. A thing does not become meaningless just because it is not the biggest thing in existence. A human life is small on cosmic scales, yes. A moment of love is small on cosmic scales. A friendship, a grief, a child falling asleep, a quiet room, a hand resting on a table, all of that is small compared with galaxies and black holes. But small is not the same as unreal. Small is not the same as worthless. In fact, black holes may help us see that more clearly, because they show us a universe in which very different scales coexist without canceling each other. The enormous and the intimate are both real. The giant black hole in the ancient dark and the person quietly listening to this now are both part of one coherent reality. One does not erase the other. The larger scale gives depth to the smaller one, and the smaller scale gives witness to the larger one. That is a beautiful relationship. A strange one, perhaps, but beautiful. The black hole does not know that we are thinking about it. And yet here we are, tiny temporary beings on a small planet around an ordinary star, able to reconstruct the existence of something almost unimaginably remote, able to reason from light, able to build instruments and theories and patient arguments, able to trace the story of a hidden object across billions of years. There is something profoundly moving in that, not because it makes us central, but because it makes us participants. We belong to a universe that can produce black holes, and also minds that can ask what black holes are. That double fact is easy to overlook, but perhaps it is one of the most astonishing things of all. A cosmos with enough depth to contain both the extreme black hole and the thinking creature, both the abyss and the question, both the hidden center and the curiosity that reaches toward it. If you slow down enough, that begins to feel less like cold science and more like a kind of quiet miracle. Not miracle in the supernatural sense, but in the sense of deep improbability felt honestly. A recognition that reality did not have to be this interesting. It did not have to be built in such a way that darkness could become a clue, that light could bend, that time could stretch, that galaxies could grow around invisible engines, that minds could slowly piece together the shape of things they will never touch. And yet it is. There is one more thing black holes do particularly well, especially for people listening in bed, half awake, drifting between thought and dream. They restore seriousness without panic. That is a very rare emotional combination. Ordinary anxiety is serious and small. It feels urgent because it is close. It vibrates inside the local system of the self. But black holes are serious and vast. They belong to a larger order. They remind us that not all seriousness is frantic. Some seriousness is quiet. Some seriousness has patience in it. Some seriousness comes from looking directly at reality and feeling no need to rush. That, perhaps, is the emotional tone of black holes at their best. Not horror. Not thrill. Not even excitement exactly. But depth. A kind of cosmic depth that makes rushing seem less necessary. You can think about a black hole very slowly. In fact, the subject almost demands it. It is too large for haste. And once the mind accepts that slower pace, rest becomes easier. This is one reason the phrase, explained slowly, fits the subject so well. Black holes deserve slowness. They deserve room. They deserve silence around the edges. Not because they are fragile, but because they are so dense with meaning that a rushed explanation can only skim the surface. To think about them properly is already a kind of meditation. Gravity, light, distance, time, growth, mystery, humility, perspective. The mind moving among those words slowly is very different from the mind scrolling, refreshing, reacting. It becomes less jagged, more continuous, more willing to be a witness rather than a manager of everything. And perhaps that is where peace enters. Not at the point where black holes become less strange, but at the point where we stop needing them to be less strange. When we allow reality to be larger than our habits. When we let mystery be structured rather than threatening. When we recognize that the universe can contain deep darkness without becoming meaningless. When we see that what cannot be escaped can still be beautiful from far away. When we realize that the most extreme things do not have to be close to influence us. Sometimes their greatest gift is simply to restore scale. If this journey through the darkest and largest corners of the cosmos has brought you any sense of wonder or calm, this is a gentle moment to subscribe, like the video, and leave a comment sharing where in the world you're listening from tonight. It is always a quiet joy to imagine these thoughts traveling out into so many different bedrooms, cities, quiet roads, rainy nights, and sleepless hours. And now, as we come to the true end, perhaps the kindest thing to do is not to force one last dramatic conclusion. The black holes have already done enough. They have shown us that the universe can build giants. That darkness can become luminous through the matter around it. That time is more flexible than it feels. That galaxies may grow in conversation with invisible centers. That our best theories are powerful, but not final. That mystery survives explanation in the best cases. That human perspective can be softened, widened, and calmed by contact with something much larger than itself. So maybe the final thought is simply this. The most extreme black hole ever found is not only a record and a catalog. It is not only a number. It is not only a giant in the dark. It is also an invitation. An invitation to think more slowly. To accept larger scales. To feel wonder without demanding ownership. To let the mind drift beyond the small walls of the day. To remember that being tiny in a vast universe is not always frightening. Sometimes it is freeing. And if you carry nothing else from this journey, maybe carry that. That the universe is immense, yes. Strange, yes. At times violent, yes. But also coherent. Also beautiful. Also knowable in part. And that is enough. Enough for wonder. Enough for humility. Enough for peace. So tonight, as you rest and let the mind go quiet, somewhere out there the ancient light from a quasar is still crossing space. Somewhere the giant black holes still sit at the centers of galaxies, holding matter in their grip, shaping the flow of gas and light, bending the paths of time and starlight without ever needing to announce themselves. And here, on this small world, in this brief human hour, you have thought about them. That is a beautiful exchange. The dark keeping its distance. The mind reaching anyway. And maybe that is all the universe ever really asks of us. Not to conquer its mysteries. Only to meet them with enough patience, enough honesty, and enough quiet wonder to let them change the scale of our thoughts. Rest now. The black holes will still be there. And so will the questions. But for tonight, it is enough just to know that reality is large, and that you are safely here beneath it, listening.